All right, so I'll introduce myself real quickly. I won't take the full half hour. I'll be as quick and factual as possible. I'm actually looking forward to the other presentations, and I don't want to hug the mic. I'll give you a really brief background on myself just because I'm a little bit of an oddball in the academic field. I'll propose a meditation and then get to the meat of it. Real quickly, many of you know me, some of you don't know me. My name is Marc Fleury. I'm Franco-Spaniard, born and raised in Paris, moved to the United States to do my theoretical physics work at MIT, left the field to go into industry. Silicon Valley was one of the pioneers of the open source movement back in the days, wrote many layers of the internet in standards, sold a company to Red Hat for beaucoup money, which allowed me to basically F off into the sunset with my family, which was great. In retirement, I went back to my first love of physics through gravity. While at the Polytechnique in Paris, my thesis advisor was Alain Aspect of the Bell experiment. So very, very early, in fact, as soon as I heard about dead and alive cats and all that jazz of the Copenhagen interpretation, the one who was helping me make no sense of it was Alain Aspect. So very early, immediately I encountered the Bell nonsense. And Alain Aspect was really interesting because he, even though he did the experiment, he was not one to push the interpretation of Copenhagen, unlike, say, Anton Zeilinger, who really delights in the magic of it all. Alain was very cautious about it all. Eventually, gravity actually brought me, of course, to field theories and all of that. And quantum was for me the thing that needed to emerge. I consider gravity fundamental and quantum sort of an emergent phenomena in a particular length scale, as opposed to saying that randomness is fundamental to the universe. I do consider that the map is deterministic chaos between deterministic equations of gravity and quantum, but that's outside the scope of this. I've published in computer science, vacuum technology. I'm not an academic, so this is all as an independent now. Now I focus on quantum. Of course, the walkers of Professor Coudet and Faure. I've financed research at John's lab, at Emmanuel's lab, other research University of Nebraska. And I try to contribute myself as much as I can. I really focus on ontology of quantum mechanics, purchased a rig to do experiments about 5 years ago and spent most of COVID conducting an experiment that was informed by the Walker ontology, and I'll cover this. This is what this presentation really is about. Aside, I do a lot of arts, a theater piece and music called The Church of Space, which is about meditation. And now that we have had time to let people in, I would like to actually start with this quick meditation. It won't take long, but it's an introduction to what we're going to talk about. And this is a meditation we do in public with The Church of Space. It's called Everything is Connected to Everything. I will ask that you close your eyes. You don't have to participate, but if you do, play the game. We're going to take 3 deep breaths and then I'll talk. Breathe in. Breathe out. Breathe in. Breathe out. Breathe in. Breathe out. This meditation is called Everything is Connected to Everything. Realize that everything, you can open your eyes and realize that everything that is in your field of vision is there because a wave, a photon has reached your eye. Everything that you see is energetically connected to the pointy space where your eye is. Visualize the pillars of the creator, the pillars of creation in this James Webb telescope picture. And realize that at the point where the telescope is, every little thing that you see here, even from the end of the universe, has sent a packet of energy that is detected by the telescope. Everything that you see in this James Webb Telescope picture is connected to the telescope. The telescope moves, we still see the picture. So everything is connected to everything. This is what every mystic says, but physics in electromagnetic, we don't need to get very fancy, says exactly the same thing. The whole universe is connected to you right now, even if you don't see it. So in theory, there is no separability. We cannot isolate ourselves from the rest of the universe. In practice, the speed of information is limited. It's the speed of light, and we're going to achieve separability. This is what Bell is about, end of meditation. Let's get to the physics. Einstein and Podolsky wrote their famous paper, and Einstein actually lamented what he called the erudite presentation of Podolsky in how he presented the paradox. And Einstein liked to couch the argument of Bell in terms of course, the finite speed of information, which linked to special relativity. Einstein liked to say, look, if there's a finite speed of light, then we can achieve isolation of the system. All we need to do is to put enough distance between the subsystems, and when we do so, we achieve separability. For Einstein, the argument of EPR was truly one of separability of subsystems. This was also linked to causality in the mind of Einstein. Bell, as you know, translated these thoughts into a theorem, and the key line in the derivation of Bell's theorem is the separability of probability, which simply states, imagine that you flip a coin, head and head, the two events together is the factor of the independent probabilities, because the events are not causally connected. They are separable. Therefore, the probability of having head and head is 1/4, meaning 1/2 times 1/2 the probability of the independent events. The factorization of P, probability of A and B equals probability of A times probability of B, is the mathematical translation of the fact of separability. Bell's theorem, for all the blah blah we go through, is actually hinges on this key line. If we have separability, the Bell theorem is actually fairly simple, mathematically speaking. If you can factorize PR, A, and B at the two separated points, then a quantity called S has the numerical value less than 2. This is Bell's theorem. A key logical insight I hang on to and hang my hat to is what I call the Nobel it's a corollary, really. But I call it the Nobel theorem. It's a two-way pun that I'm very proud of as a Frenchman. And it's basically the logical inverse of this statement. If separability, then S less than 2, the logical negation of this is if we observe S strictly superior to 2, it means we have no separability. So if we were to take Bell's theorem at face value and the logical implications of it at face value, the Nobel theorem, which is a corollary, the logical negation corollary of Bell's theorem, says if we observe a violation, it means we're not separated. For if we were separated, we would not have S superior to 2. So why is this so magical? Because so far it's a fairly easy story I've been telling. Well, it's because the Copenhagen actually talks about isolation between the detectors. And we observe S strictly superior to 2 in modern Bell experiments. 2 of them are schematically represented here. And the story with which we wrap this result is very magical. And it's a story about isolation between the detectors. We isolate the detectors. And so on the face of it, Bell is a really, really puzzling proposition, because the Copenhagen interpretation tells us, well, you have this wave function, which may be mathematical in nature, just describing probabilities, but the probabilities realize when we have a physical action at one detector, which collapses the wave function with a laser. And at the other end, something magically happens regardless of the distance. And when we isolate physically these two systems, we still have this result. Well, that's a very magical story. And if you look at, so to the left of your screen is the usual schematics that you have, where you have the beam splitters, little a, little b, the detectors d minus, d plus on both sides, and the coincidence monitors. On the right, you have a very, 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 very fancy version of this. This is one of the latest experiments by the Zeilinger church, I should say, about 100 kilometers of submarine fiber with very fancy PBS. I'll go through some of these equipment that they talk about. I will point out, and this is really the gist of my argument in experiments and really in reviewing their experiment. By the way, I sent my paper to Gregor Weiss. Gregor is the one who did the experiments for Zeilinger. Right? The very first Zeilinger experiment was done by Gregor Weiss when he was a grad student with Anton. Gregor is now a full professor at the University of Innsbruck. And I've had long exchanges with Gregor about this experiment. He corrected many, many things, but basically he agrees with what I'm presenting here about his own experiments. As you know, they got the Nobel for it, but I'm going to make very clear claims. I'm simply going to claim that there is no separability to the source in these experiments. The source is never separated from the detectors. The detectors are always set. Bell famously prescribed that we should set the detectors in flight. Okay? We send the photons from the source, and then boo, 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 we move the detectors, we set them, and we make the measures. That's physically impossible. We don't have the actuators to do that physically. We just can't do this experiment. It just does not exist. By the way, I read Gregor's thesis in German by putting paragraph by paragraph into Google Translate. That was a fun week of my life, just reading through his German and the thesis with Google Translate. I should do ChatGPT now. But basically, even Anton says this, we cannot do the actuator. So what we do instead, in Aspect and Zeilinger, what we do instead is we put this AEOM, which is actuators, acousto-electronic optical modulators, that switch the path of the photons, but we set the detectors in a preset fashion. These settings in the Nobel-winning experiments are static. We do not change the settings in flight. The settings are always static. What we change in flight is either the amplitude in the case of Aspect, I'll show that in the next slide, or the phase in the case of Zeilinger, but at all times, the source of the photons has visibility on all four settings. At all times, there is no isolation from the source to the detectors. There is isolation between the detectors, which satisfies the Copenhagen narrative. But with Paul Verbos, I will argue that we're probably looking at something more simpler, namely that the source is influenced by the detectors. And that would very simply explain why those photons seem to know what's going on. It is because they know what's coming. This slide is actually a deep dive into, well, a dive into the AEOM components and why this claim of isolation in the narrative of the Bell-Winning experiment is false. It's true of detector to detector, but it's false from source to detector. To the left, you have the acousto-electro-optic modulator of Aspect, and to the right, you have the phase modulators of Zeilinger. The ones to the left, it's a Puckle cell that has a transducer that induces a current and creates acoustic standing waves in the media, and this acts as a mirror. So you have a megahertz oscillation of the mirror in the aspect. But if you look very closely to the transmission, the transmitting and the deflected, you never have a true zero. Okay, this is true even of today's state-of-the-art acoustic optical modulators. You always have a residual signal, even with the state-of-the-art 2023, of about 15 to 20% residual signal. That's huge from an optical standpoint. Okay, there is no isolation. The source always sees through this transducer the 4 detectors. So put your eye at the source, look down to the IOM, see a mirror, and see 2 superimposed detectors. You see the 2 superimposed detectors on average with the same intensity. You have 0 isolation from the source to the detectors. Let's look now at the phase modulators of Zeilinger. What they do is they introduce a modular phase varying in the gigahertz by electric signal in electro-optic modulation of a crystal, which induces a phase delay, which switches the path of the photons. But again, it's fully transparent. Amplitude 197%. Huge signal. What we change is the phase. So on average, the source always sees the 4 detectors superimposed. There is no isolation from the source to the detectors. Of course, the story of Copenhagen, let's go back 2 slides, and then I'll go to the experiment I did, and I'll take 5 minutes and we'll be done. Of course, the story of the Copenhagen is very magical because it focuses on a hypothetical collapse of this very magical wave function that happens at the detectors. When we detect at Alice, there's a projection at Bob. So there's a causal story of separability that, of course, clashes with Bell's theorem. But this is linguistic. This is actually a paradox of linguistics and just the wrong ontology, the wrong interpretation. The Copenhagen talking about dead cats and alive cats, of course, does not mean anything. So if we have no isolation from the source, these red arrows say the source always knows what's going on at the end. Even with the modulation of the phase and amplitude in the middle, on average, we have a standing wave of, say, like Faraday wave of the walkers, cavity resonance. Then there is no magic here. The system is not separated. We should, in fact, trivially violate Bell. I have personally run simulations of walkers in Bell. John has written recently with Álvaro a great paper on isolation of Bell violation in walkers. We're looking at systems that are not isolated. We have a signal from one detector to the source or the other. And when you have no isolation, by the no-Bell corollary, you should see S strictly superior to 2. The magic is all in the narrative, not in what's going on. With that insight, while I was at the Parisian Langevin with Emmanuel Faure, we came up with this experiment in a classic Bell setup. And what this experiment is, okay, well, if the source is not isolated from the detectors, let's put this rotating Foucault mirror in the middle. And Foucault mirror is a rotating mirror. Foucault used it in 1860-something to measure the speed of light in Paris between Montmartre and I think La Sorbonne. And basically, we bought a state-of-the-art Foucault mirror. This is actually, I had to sign papers that I was not using this for military application and who the hell I am to buy this mirror, blah, blah, blah. It's 1,000 hertz, so 1,000 rotations per second, state-of-the-art. And what that does is you have the source in the bottom center. I apologize. I don't know if you see my mouse here. Do you see it? Okay. So this is the SPDC source, and we have 200 meters of fiber on both paths. And the Foucault mirror is rotating so that the line is moving. The mirror is bouncing and the line is moving. So only very intermittently do I go through this aperture, through my polarizers, and through my collector. So in the event that the signal is from detector to detector, This isolates it and even isolates the source to the detector. I don't know what my linear polarizer is going to be instantly. Okay? If all of a sudden this opens, even if I have an instantaneous signal, I cover that. The 200 covers instantaneous signal. I don't have enough time for the photons formatted by this information to reach my detectors. So I create strong amplitude isolation in the Bell setup. Of course, my hope was that we would lose the Bell violation. I called it the no Bell experiment. Good pun. Instead, I observe it. It took me 4 months of going crazy. I did this during COVID. It's not easy to do it. I literally do this in my closet. I have about $250,000 of Zeiss equipment in my closet and do all this crap. I've killed more fibers than I care to. I'm naturally not a great experimentalist, but I taught myself and I'm now a more than decent experimentalist. I'm very proud of that fact. But anyway, I observed a clear violation. All right, well, that's weird that I observe a clear violation. How can that be? Because I'll go back one slide for 1 minute. If you know, even if this is open and I have a signal that says, hey, cheat, I'm going to measure you along this angle, and over here I'm going to measure you along this angle, so I'm constraining you, crystal, so now you can send me photons that correspond to this violation. The time it takes for these photons to fly back by the fiber is such that I don't detect them. So it cannot be an instantaneous signal, period. So I invalidate all classes of models that are based on a field. I'm looking forward to the next presentation that do not, need a field to arrive at Bell violations. But because I do this isolation, I eliminate all classes of traveling signals. But I'm not completely isolated. I intermittently see the target. So could it be a standing wave? To the right is the pictures that actually gave us the idea when we were doing the Bell experiment in walkers at Langevin in Paris. This is a Faraday field. It's always there in the walker. It's a background field that really translates the cavity in a way for you. Of course, the difference between the standing wave and the traveling waves is well known. It's those two diagrams. You can always have a standing wave that on average is there in the field, in the cavity, in the Bell experiment. I do not rule these out in my own, but I do rule out all traveling waves, including instantaneous signal. There are many properties of the standing waves that are very interesting. Well, first of all, that was the Louis de Broglie hypothesis. He took his wave duality, he hypothesized matter as standing waves, and hypothesized a Zitterbewegung clock, a movement, the Zitterbewegung, the little vibration that gives us Compton standing waves. And it's interesting because if you Doppler shift it, you have a law in contraction that is proper to the standing waves. This is not generic. It's not true of only traveling waves. You need the forward and backward traveling. But when you do that, you have a beating effect on standing waves by Doppler. And it so happens that the math, the bridge between the two, is very specific. You go from Compton standing wave to de Broglie standing wave by a Doppler contraction and expansion of the component traveling waves. This is, I've stolen the graphics to the right from John Macklin, who's part of our group and has presented to our group, where you see contraction one way, contraction the other way, and the sum is a standing wave with a moving de Broglie node. Okay, and it's a necessary, logically speaking, condition in this case. First, that we have a standing wave, and number two, that the standing wave be at Compton, meaning an electron standing wave. So we may be looking at cavity effects standing waves in Bell. Therefore, could we interpret Aspect and Zeilinger with just phase effects? Phase on standing waves? Mind you, for me to maintain 400 meters of phase coherence across the fiber, meaning the cavity resonance across the fiber, took me months. It's really hard. I'm amazed that Zeilinger and company can do it over 100 meters with just one bat ear setup. I'm amazed that the Chinese can do it with an orbital station. That kind of experimental coherence is non-generic and really, really hard to do. So those experiments are remarkable, but they may just be phase effects. Also, if we were talking about the quarter wave plate experiments I do with verbose, but if you look at the formalism and you put a half wave plate in the middle, it disappears. The Bell effect disappears. Well, how I did that? I actually put a half wave plate in my setup, just, oh, let's put the half wave plate and see what happens. It disappears. How interesting. Because if you're talking about particles, why would a half wave, like little quarter or half wave, completely change what's going on if they're particles? Makes no sense. In fact, our setups are not that precise. It's just rig on a breadboard that blah, blah, blah. It doesn't make any sense. But if it's a standing wave, then half a wave plate will completely destroy my signal by destructive interference. End of story. End of story for me. And I've done this, and Bell disappears with half a wave plate as the formalism dictates. And 10:29, I'm right on time. I started with 2 minutes or 3 minutes late, so I don't know what you want to do, Jarek. We can take a couple questions or just move on.
Sure. So if there are some questions, remarks, please ask, and maybe you can stop sharing, and Richard could share and start. So.
And
well, I did write in the chat that I think your summary of what Bell assumed is a little bit cutting it short. He did not just assume probability of A and B is probability of A times probability of B. He assumed something rather complicated concerning the interaction between 4 binary variables, third order interaction.
The hidden variable thing is a narrative. It's blah, blah, blah. The real meat of his...
Yeah, it is for me too. I mean, I don't believe in hidden variables, but the experiments disprove hidden variables.
No, it's just a story we tell with the hidden variables. The real meat is separability. And Einstein says it's separability. And the separability...
Oh, we will continue to discuss.
No, I'm happy sending the actual line from speakable and unspeakable. It's one line where it shows that, and once you have that, the rest of the math is straightforward.
Yeah, I know it's utterly trivial maths.
I don't see the chat. Oh, I do see the chat. My bad. Spooky observation.
Mark, I was wondering when you were talking, where did you put the half-wave plate? Because in the experiment I run, I have on one path, like the quiet Zeilinger experiment, you know, of 90 something. In one path of the Bell experiment, you put a quarter wave plate and a half wave plate, and that allows you, by manipulation of the angles 0 and 100 in the phase element of the wave function, you can manipulate that alpha, that phase, by a wave plate. So this wave plate will create either a psi plus or a psi minus EPR Bell state. You prepare the system in that way, yeah? But you turn the system into a phi state, phi plus or phi minus, by putting a half wave plate before the half wave plate and doing similar manipulations with angles. So I'm investigating that, but because I'm investigating that, I didn't know exactly where you put the half-wave plate.
Right. Let me. The psi plus psi minus is by putting a quarter wave plate in the pump. That's one thing I can put in and out of my QTools setup, so it's fairly easy. I always work in psi plus, and it's actually downstream. So in the measuring section, not the source section, but the measuring section. If you put a half-wave plate, it disappears. By the way, the math of the Copenhagen formalism says as much. Put a half-wave plate, the whole thing goes to 0, right? So the formalism is not wrong. It's just the story we tell about the formalism that is nonsense. And, personally, I consider all of these paradoxes, including the delayed choice, why the particles know what's going on, because you have standing waves that tell them. It's like echolocation, really. This is what's coming on in your future. To me, all the paradoxes are proof by the absurd that the narrative we tell is BS. And the half-wave plate, again, is okay with the formalism. It's a 5-minute experiment once you have Bell going. It's not really complicated. The complicated part is getting all those phases in order to observe Bell. But once the phases are perfect and you put half a wave plate and you move the thing, it goes to zero immediately. I mean, that's a 5-minute experiment. I encourage you to do it if you got the thing doing.
No, I've done it. I've done that. I've done
Yeah.
that. But I'm wondering, my question was, where do you put the half-wave plate? Because in my
I
experiment,
repeat, I put the halfway plate in one of the arms of the measuring apparatus, not in the
but I
source.
do that. And what I do with the half-wave plate in one of the arms is to shift from psi plus and psi minus to phi plus and phi minus.
No. I don't think that's correct. No, I don't think that's correct. If you put the plate in the source, you'll shift, but not downstream. I could be wrong.
I can show you the paper of Zeilinger, which he does the same. We reproduce that, and we can talk about that later. And I can show you what I've done and my results. But maybe your setting is it's a little bit different. So I don't know exactly.
In the pump from Q2, I have a quarter wave plate I can take in and out, shifting psi plus, psi minus, and in one of the arms. But that's the source, so it impacts the pump.
No, I do it on the arm.
I do it on the arm, and when I do it on the arm, you're not shifting psi plus, psi minus. It's one psi plus state, period. But I shift and it's not there, which it shouldn't be. I mean, the formalism says it should not be.
But it's interesting because I'll have to. We can get together, and I'll have to show you what I've done, and we're about to publish a paper on those results. So, and it's basically the baseline is Zeilinger experiment reproduced successfully, and then right. That's how he did it.
I'm not proof EPR correct. The formalism says this. This is not magic. We're not violating Bell or anything. This is what the formalism says. It's just that at the interpretation layer, if you look at half wave plates moving standing waves, you can see that it goes to zero, right? So our narrative is still particle because of Copenhagen. But really, if you think about this problem, just like you think about the double slit or single slit experiment, we think of the double slit experiment in terms of waves, not in terms of particles. In terms of particles, the double slit experiment doesn't make any fucking sense. You have ballistic trajectories, end of story. And if you think about waves,
I'm not questioning your.
No, I'm answering James in the chat. No, not a half wave.
So what I
think a lot of our problem is that
do you mind if I show you one diagram? Can I share?
If we have time, Jarek.
So maybe let's.
I'm happy taking it offline, by the way.
Let's try to go to the schedule and you can So there will be the discussion after. Sure.
Yeah,
I think I'm going to start sharing my screen now. If I can find it.
All right.
Thank you.
Bell mini conference. Okay, can you say this? See this? Can you see this?
Yes, very good.
Okay, and can you still see it now? I put it on play.
Yes.
Okay, right. Okay, so I will briefly introduce myself in a moment, like the last speaker, which I think is useful because there are a lot of different people here and we have many different backgrounds. Now, I'm going to try to keep this short because I am just going to tell you some terribly negative things about what I've been looking at the last couple of weeks. And first of all, there was an email from Marian Kupczynski who said, my contribution for the discussions of this session would be his paper. And I started looking at his paper, and I'm going to tell you what I thought about his paper, which won't be very positive, I'm afraid. And then there was a discussion with emails by Sergei Rashkovsky, and I don't know if he's here. I was hoping that both these people would be here. And okay, I'm going to say some rude things about what he was promoting. Now, I'm a mathematician and a statistician. I'm not a physicist at all, really. I've been involved for a long time in Bell inequalities because there's a lot of classical probability in there, reasoning, and there's a lot of statistical analysis too in the experiments. And I contributed new methodology for the experiments, which actually using in the latest experiments. Like in 2015, there were 4 experiments, famous experiments, so-called loophole free. Now, all of those four experimentalist groups, they actually cited me and used a methodology which I'd invented. And I'd love to talk about it, but I'm not going to talk about it now because I got myself into this track of these things, which you can see on the slide now. Briefly about myself, one of my main activities is getting serial killer nurses out of jail. And I should emphasize that I concentrate on serial killer nurses who are properly innocent. And this was quite amazing that a journalist of science wrote a whole article about me, 7-page article in Science. And if you want to find more about me, you know, have a look at that article. It tells you what are the things that drive me. I mean, basically, I'm driven by injustice and fixing misunderstandings of statistics. Okay, so that was a little self-advertisement. Actually, I did explain to the journalist who wrote this how my work on quantum entanglements actually helped get a convicted serial killer nurse in the Netherlands out of jail, because I went over to my colleague Gerard het Hoofd, and I asked him if he would sign a petition which I had composed, and he thought about it, and then he did, and then the next day the journalists saw that Gerard het Hoofd had signed the petition, and this was one of the things which forced the system, the establishment, to take a bunch of rebellious people seriously who were saying that her conviction was unjust. Right. So I want to talk about two topics. And the first one is this work by Marian Kupczynski, which came out this year. And of course, he thinks that what John Bell today would choose would be contextuality. And I think that John Bell today would choose non-locality, and I'm very happy with that. Okay, then the second topic, if there's enough time, see how it goes. Right. Yeah, this is sort of technical. I want to explain to you that our friend Marian Kupczynski has been writing about 20 papers the last 10 years, attacking Bell and saying that it's all a question of contextuality and not about non-locality. And I'm afraid most of those papers are wrong and they make elementary mathematical errors. Now, can you see my mouse? Or is my mouse not visible? Somebody can see it. Okay, because I here copying a couple of formulas from his paper, and of course they're sort of horrible formulas. And next thing I'm going to do is show you what his idea is in a much more simple way. But the formulas are going to be important because formulas actually show an enormous confusion of notation. So the people who study Bell's inequalities may have seen things looking like this. You have settings. Alice is setting I, Bob's setting is J. Then there are two outcomes, Aij and Bij, and one computes the expectation value under an assumption. Bell computes it under an assumption of local hidden variables, or equals local hidden variables. And Kupczynski wants to say that Bell's assumption is much too narrow and it's unrealistic and it's unphysical, because it is very reasonable to suppose that the hidden variables are not just sitting in the source, going to the two photodetectors, etc., but that they are also hidden variables in those detectors, in the apparatus, in the two apparatuses of Alice and Bob. And so he is got here, lambda 1 is the hidden variable going from the source to Alice's place, and lambda 2 is the hidden variable going from the source to Bob's place. Now, this is a bit dangerous notation because he's got lambda 1 and lambda 2, and he's also got lambda I and lambda j, and I and j are indices which could be 1 and 2. But when he writes lambda I, he doesn't mean lambda 1 or lambda 2, he means something else entirely. So this is a danger of trying to write things up in formulas when it's much better to look at it in a different way. So the lambda 1 and lambda 2 are going from the source to the two detectors, and lambda I and lambda j are variables which are sitting there in the detectors. And actually, he doesn't put this little prime here. I added that. I corrected what I think is an unfortunate misprint in his paper, because you mustn't think that I mean, if j happens to be 2, you have to know that lambda j is still the lambda j in Bob's apparatus, the lambda 2 in Bob's apparatus, not the lambda 2 which could be in Alice's apparatus, not this one, not this lambda 2. And both those lambda 2s of Alice and Bob are not the lambda 2 which goes from the source to Bob. But anyway, so there are 4 things here. There's lambda 1 and lambda 2, a lambda I and lambda j prime, and I and j can both be 1 or 2. So actually there's a lambda 1, a lambda 2, lambda 1 and a lambda 2 with a little I belonging, and a lambda 1 and a lambda 2 prime. There are 6 lambdas in his model. That's a lot. He's got hidden variables all over the place, and they have all kinds of indices hanging on them, showing that they should be interpreted in a different way. Okay, the outcomes are plus or minus 1 as usual. There is he says lambda is lambda 1, lambda 2, lambda I, lambda j prime, and it's an element of a set lambda ij. So actually we have 4 of these, because there are 4 combinations ij. So it's a horrific notation, and maybe is responsible for confusion which comes up. Here's his basic model, is saying that the joint probability density of all the hidden variables does factor into the probability density of the stuff coming from the source and the probability density of the stuff in the detectors. So here are the detector hidden variables, and here are the source hidden variables. And then one of these 2 and one of these 2 goes to Alice. One of these 2, well, I mean, this one is already with Alice. Okay, now there's some words here which I won't go into, but his claim is that his model 10 allows explaining data from Bell tests in a local and causal way. And he writes out some formulas, and he talks about all that, and claims that in this setup you cannot prove Bell inequalities, and therefore Bell is nonsense because it's unphysical, because it's all just a question of contextuality. Now, I think it makes good sense to try to look at this graphically, and in statistics and probability and causality nowadays we use graphical models a great deal, which is we draw simple graphs of special type, directed acyclic graphs explaining the dependence between a heap of random variables, some of which may be observed and some not observed. And so there's some lines of text there. The thing about a directed acyclic graph, here's an example. This directed acyclic graph is actually a representation of the formulas of Mr. Kupczynski in a graphically, in a visually, which explains how he thinks everything is going on, what is created in various places, and then goes to various places, and then things are made out of what came. So he starts off here top left with the settings, I and J. Alice gets a setting and Bob gets a setting, and he allows them to be statistically dependent. I'm not concerned by that. That's certainly allowed. Over here, he has, so there's the settings that are coming perhaps from the experimenter or experimenters. Over here are the hidden variables in the source, one of which goes to Alice's side, and the other one goes to Bob's side. They're lambda 1 and lambda 2, not to be confused with lambda I and lambda j prime, which are the hidden variables in the instruments, in the apparatuses. And he says they may be correlated. They are independent of these ones. So the graph says, the model says I and j are independent of lambda 1 and lambda 2. Given I and j, these things in the middle have some probability distribution depending on I and j. Now we can move down. then this node of the graph says that given the arrows coming into it, so given these variables and these variables, this is some possibly random function of the values up there and over there. Now, it's a little bit complicated and confusing, and I already kind of fixed this notation by putting a prime here, so we would know that this lambda j prime belongs to Bob's instruments. Oh, I'm not quite sure if you can see it. Yeah, what he keeps saying about his model is that the I and j, so the actual settings which are chosen are dependent, statistically dependent on the instrument hidden variables. And not only that, if you look at this graph, you start with the settings, then you go to these variables, and you, then you go down to the bottom. There's an I here, and there's a j here. So this thing here, A, is a random function of I and lambda 1 and lambda I, and this B is a random function of J and of lambda 2 and lambda J prime. So that's, and that, I've added IJ there. He doesn't say that that's what he's doing. Well, he says it implicitly by the line up at the top, which I can't see because there's something in front of it. Anyway, he's assuming that the settings go to the instruments, because they have to be available to the two instruments separately. And he said that they can be dependent, and he said that these instrument variables are dependent of those. So what he's well, to see that this is nonsense is to see that you could model any correlations between the observations given the settings you like with that model. That model makes no restrictions whatsoever on reality. It's more general than quantum mechanics. Basically it's a violation of locality. He's saying the settings are known throughout the whole experiment before the experiment is done and influence the variables which are in the various locations. So, well, maybe Marc agrees with that because this could be the standing waves doing that. But it's silly, and I won't say more about that. But what I do want to say is that there is an enormous amount of confusion in the literature, and people are making things much too complicated by making extremely complicated stories about things and not keeping them simple. So a similar topic is some more recent work. There are various people out there who are saying, well, I'll show you what they're going to say, what they say. Sergei Rashkovsky, we had some emails from him recently and discussion with him, and he drew attention to some papers of his. De Raad, Michielsen, and Hess, possibly famous or infamous, I don't know. De Raad, Michielsen, and Hess, they want to introduce a new loophole. Now, I'm getting worried what the time is. Well, it seems I still got 10 minutes, so that's okay. De Raad, Michielsen, and Hess have decided to introduce a new loophole, and it's called the photon identification loophole. And their idea, their idee fix, is that these experiments are about photons, and more specifically, they're about pairs of photons. And we have to look for and restrict attention to pairs of photons which were emitted at the same time, which therefore might be entangled or correlated or whatever. And if we don't make any attempt to identify which of the events which occur in these experiments belong to pairs of photons which belong together and which events don't, then we're wasting our time. And I think this opinion, which actually is quite widespread, I show you that the other guy, Rashkovsky, has got the same idea, is based on a simple misreading of what Bell was on about, what he was trying to do, what the experiments nowadays do, and people should take account of this before saying that Bell was wrong or whatever. They say it is essential that the identification of photons is included into any meaningful theoretical model of an EPRB experiment. Otherwise, the model is too simple. Failing to do so, only spooky influences can explain the observed pair correlations, specifically omitting the inclusion of data which select the photons and or pairs opens an Einstein local loophole, which we call henceforth the photon identification loophole. And they say by design, Bell-type models for the recent experiments that claim to be loophole-free suffer from this loophole. Now, I think they have not read the papers of the recent experiments because that is simply true. So they believe a myth and they have been misled by what Aspect did long ago or Clauser did or whatever, and they're not taking any notice of what the experimenters are doing today. That's one of my messages. All the people talking about what was wrong with Weiss' experiment or with Aspect's experiment or something, please just wake up and take a look at the experiments which got the Nobel Prize. They are doing rather different experiments. They are also aware of all the issues which enable one to give alternative interpretations of aspects or Gregor Weiss, who's a friend of mine as well, by the way. Gregor Weiss, I read a paper with him even, Gregor Weiss experiment, yes, it is vulnerable to a loophole, which means the results could mean something else than what some people would like it to mean. But there has been a lot of progress since 1980 or whenever it was, or I forget exactly when, or 90. A great deal of progress, and it's progress by experimenters who are aware of the defects of the early experiments and have come up with extremely original and exciting and interesting new technology in order to neutralize those defects, to eradicate those defects. So with the experiments we should be talking about is not Aspect's experiment in 1980, but the latest experiments, for instance, of the Munich group, the one published in 2022 in Nature, fantastic experiment. It's completely different, or completely different type, and it's not open to the explanation, I think, which some of you guys would like to give them. I mean, I'm happy to be proven wrong, but you are fighting, dead cows or something. I forget the good saying here. This is what de Raat and Michelson and Karl Hess say. They say specifically a physical theory that describes pair correlations of space-like separated systems must account for and include all procedures that determine the detection of the particles and the knowledge which pair of particles and data belongs together. That's what they say. Maybe many experimentalists would say that's obvious. Yes, of course. Well, I say that's not obvious. It's not obligatory. There's no must. And Bell absolutely explicitly made it absolutely clear that you shouldn't do that, not to do what he wanted to do. Of course, if you want to study photons, you're going to assume things about photons. But if you want to study local hidden variables, you're not going to assume anything about photons. Rashkovsky has exactly the same mentality. He notes that in the results of real experiments, all kinds of things play a role. He doesn't know about the newest experiments where they no longer play a role, and so on. He's got the same idea. I think it's a wrong idea. So yeah, who says you have to analyze experimental data in any particular way? You may analyze experimental data in any way which is meaningful. And Bell experiments are done for a particular purpose. And the good experiments nowadays are designed in order to give clear answers to the questions connected to that purpose. And the experiments should be analyzed in that way. this was a little figure of Bell from the Bertelmann Socks paper, one of my favorite papers. And what I have written there at the bottom is the aim of the experiment is to test the hypothesis of local hidden variables being the mechanism which is describing what is going on inside that long box. We don't want to and don't have to. There's no need to think about what is going on inside the box. The question is, could what goes on inside the box be of a certain form? And Bell shows that if it is of a certain form, then there are certain inequalities will be true. Experiments violate those inequalities, and that means what is going on in the box is not of the type written at the bottom, on the bottom line there. And Bell has some words in the paper there, which I like rather much. He says, you might suspect that the very notion of particle freely used above has somehow led us astray. Did not Einstein think that fields rather than particles at the bottom of everything? The following argument, and that's the derivation, will not mention particles, nor fields, nor any picture, whatever of what is going on at the microscopic level. It will also not use the word quantum mechanical system, which can have an unfortunate effect on the discussion. So forget about quantum mechanics too. The difficulty is not created by any such picture or any such terminology. Those terminologies and those pictures are irrelevant. It is created by the predictions about the correlations in the visible outputs of certain conceivable experimental setups. And these are conceivable experimental setups, which are actually performed nowadays routinely, and in which one sees violations of those predictions about the correlations, and therefore you can conclude that this picture of what is going on is wrong. And if you don't care about that picture, then you're not interested. I mean, Feynman was not interested. He already knew that this was not the way that things work. Okay, I think I can skip that slide. And this is the last slide. Okay, so no, I'm being annoying. So Planck's principle is that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it. And my comment is this is taking a bloody long time because the misunderstandings about what Bell was trying to do and what indeed the purposes of the experiments which led to the Nobel Prize last year, a lot of people still don't know and haven't bothered to find out, and then we get interminable waste of time. I mean, noise, confusing the young people, etc., etc. So that's what I wanted to say. Thank you. What is the time? 1 minute past 5.
So maybe some question, comments. And I will switch to mine, and we can discuss for a minute or two.
I have a quick question, General.
And who's that? Yes, Adam. Okay,
my name's Adam. Can you see me? Okay.
Yeah.
So I appreciate your engagement with the Bell deniers. I'm aware of some of your other work, and one thing I've not seen you write about, and I'm curious to know your opinion on it, if you're aware of it, is the literature on compatibility, probabilistic compatibility, and Carl Hess has written a little bit about this.
Yes.
Phillips.
Yeah,
right?
yeah.
And I think in particular, there's a paper by Itamar Potowski which associates the Bell mathematics with actually going all the way back to George Boole. And
I know.
And I'm curious to know what you think about that, because in my opinion, that makes most sense in light of what you just said about the Bertelmann socks and Bell's comments about, we don't need to know what is happening inside the box.
No. Yes, I know that literature well. And I think Carl Hess is a muddled person. I mean, he's a kind of a giant of his field, which was quantum electronics or something like that. And I think he just does not understand Bell. And I think I do. I'm sorry. I mean, I come from Ireland too. I mean, John Bull came from Ireland, Bell came from Ireland. My grandfather's grandfather left Dublin for England at the height of the famine in 1850. So I have Irish blood too. So I appreciate Bell very much. And indeed, Bull proves, you could say, proves Bell's theorem in his book. I'm one of the few people who actually check the proof in there. And lots of people say this. And so the thing about compatibility is, the hidden variable assumption, the local hidden variable assumption is the assumption that a probability model with various variables all existing can describe the situation we have in. So Bell called it little lambda. I'm a probabilist. I call it little omega. I mean, it's just Kolmogorov's omega, and it's not like the physical cores or the physical variables, hidden variables, but it's just a kind of enumeration of all the possible outcomes. And so the answer is yes, but we already know that quantum mechanics can't be modeled in this way. It allows correlations which are not allowed in a classical way in a certain sense.
Okay, so maybe let's take it to the end, or we can continue to chat, for example.
Yeah. So I should stop sharing.
Yes, I have already started. Do you see my slides? Right.
Yes. Oh, you've already stopped me sharing. Great.
Okay. Yes. Thank you. So I'm sorry because I have a lot to tell as always. So that's the big problem that we successfully use Lagrangian theories, general relativity, electromagnetic quantum field theories. So, but they are hidden models. So can we do it in view of Bell? So my answer is that yes, we can. The problem is that we use this intuition of time present is that we have this current moment, and it evolves in future toward future according to the Euler equation or let's say Schrödinger equation from the simplest perspective, but that this is not correct view. That physics instead has solved the equations through the eternalist block universe point of view, which is natural for general relativity. That, for example, solving to the least action principle instead of Euler-Regular. So one can say that we can translate between such solutions. However, if the solution originally found with each of them have different properties. So the ones on the right, this action, have superdeterminism. They know about all the future measurements, you can say. So this is kind of living in space-time as a four-dimensional jello, that each moment in time is in equilibrium between past and future. And for example, in S matrix, there is this well-known formula that you have two amplitudes. One is past, second of the future. So that's very natural in many perspectives, a way to get the Bohr rule, that one amplitude goes from symmetry, one amplitude from past and future, and second from future. So to show it, I will talk about the Ising model, which is kind of simplified view on this Feynman path ensemble. So Ising model is also path ensemble, but now in time instead of in space instead of time. Feynman is in time, and it is weak rotated, simpler to understood. So I focus on this random walk along Ising model. So here we have the Kolmogorov third axiom on the left, which leads to Bell inequalities. But on the right, we will get Bohr rule also in Ising model, so which allows to violate Bell-like inequality. So we replacing this simple equality with this sum of amplitude squares, the probability. There is some noise. So please, somebody's controlling. I don't have control now, so please. Okay, so a big problem for them, this deterministic view is then the measurement. Can we? There is some noise. Could you mute? So there's a big problem with measurement. So with this non-unitarity of quantum mechanics, like measurement. So can you understand it in deterministic way? So Tankersley is a nice idealization of measurement. So it is that magnetic dipole aligns in external magnetic field, getting to make the torque zero. Torque is is magnetic dipole cross the external magnetic field. So this being zero means getting parallel or anti-parallel alignment. So otherwise we have Larmor precession like here, which means additional kinetic energy. So non-aligned has additional kinetic energy. Like excited atoms want to radiate this excessive energy as a photon, for example. So Manfred, there is some noise from, if you can mute. Okay, thank you.
I see still your conclusion on the page with conclusion Planck's principle. Is it only on my screen or?
Sorry. So can you see my? So let me try one more time. And now, do you see my first slide, second slide?
Not yet.
Yes, second slide. Yes.
No, I see only black screen.
Can anybody see my first slide, second slide?
Yeah.
Everybody else can. I
can
think
see.
you may have a slow computer.
Second
or a
slide,
computer
okay.
issue.
Okay, so here is a second slide about the Stern-Gerlach. So if the spin is not aligned, then we have this additional Larmor precession, the additional kinetic energy, and excited like atom has tendency to release this energy because there is no going back if it escapes to infinity. So unaligned spin has additional kinetic energy of Larmor precession. Also, this alignment also changes the angular momentum because it is along the spin. Also we have this pointing this energy density radiated. So having magnetic dipole which is staying, then the electric field is zero. But it start precessing, then it's got a non-zero from Maxwell equation. So we get some radiation of energy, and so naively the question is, can we observe it? So while the exciting of atom, we get a photon which we can absorb. But in this case, we have cylindrical kind of antenna, and cylindrical antenna produces cylindrical electromagnetic wave. So it dissipates 1 over the density 1 over distance square. So it might be much more difficult to observe. It mostly turns it into heat. So also it is kind of the deterministic on this measurement as Stern-Gerlach, and it could be also reversible, but the problem is that we would need to prepare reverse electromagnetic wave, which is very technically challenging. Okay, so let me go to the main topic. So I will talk about this random walk along Ising model, Ising sequence, for example. So the question is, so this is called maximal entropy random walk. And so the question is, why should we maximize entropy? So this is, I use this simple view. So having these n positions and with zeros and ones. So the question is, how many sequences are with some percentage of ones? So there is this asymptotically, it's 2 to power entropy, Shannon entropy of this probability. So focusing of some chosen probability, we restrict to subspace of possibilities with this percentage of let's say 1, and this is the largest for this percentage being 1/2. So this subspace dominates combinatorially all the remaining possibilities. So this is the simplest view on this giant principle of maximal entropy, that if we don't know some parameters like this P, the second assumption is to choose the one which maximizes entropy, because it corresponds to subspace of possibilities which grows the fastest with the size of the system, this n. Yes. So now let's briefly look at this thermodynamics, the classical mechanics. So looking, for example, at this system of this containment with some particles on the left. So from classical evolution, it should be nearly cyclic to the Poincare recurrence theorem. It's deterministic. We have single possibility. So entropy is 0. So how to get entropy? Some statistical mechanics. So we need to perform this approximation. It's called, it can be viewed as mean field, as Source-Zern-Zatz approximation. And after this approximation, we can get the entropy growth, because before we have entropy 0 all the time. So here is approximation of this setting, saying that we say that you have just one value, P as percentage of how many percentage particles are on the left, as the entire description. Using this simple description as just simple number P, then we can derive entropy growth. So to get entropy growth, you need to get to the statistical picture, like this averaging over to get the density. And after doing that, we can derive entropy growth. But before, we can get Poincare recurrence theorem, going back and back to the same situation. And there is this nice Katzring model I recommend, which is kind of similar to what I have told, that we have these black and white balls, and we get one step around, and there are some mark positions. Going through this mark position, you get black to white or the opposite. And so using simply this Stozer result, this mean field approximation, you can easily show that entropy should grow. However, if you do the deterministic, that after making 2 rotations, you get the same color, because you get even number 2 or the position. So the entropy grows, then it behaves cyclically. Very nice simple model. I recommend to look at to understand how the entropy grows in time symmetric models. This also can be time symmetric model, H theorem. Okay, so let's go to this random walk along Ising model. So this is this maximal entropy random walk. So there is a big question how to choose probabilities in random walk on a graph. So we have a simple graph, ones and zeros, and after 1 we have to use 0. After 0 you can go 0 or 1. So for a random walk we have one parameter, this Q, which decides what is the probability of going to 0 after 0. The question is how to choose this Q. Yeah, so in standard random walk we would say that Q should be 1/2, because 1/2 maximizes entropy. However, it turns out it only maximizes entropy locally for this one step. But taking mean entropy, we don't maximize it for 1/2. You should use 0.6118. This is the entropy maximizes entropy, and the probability maximizes entropy. This is the entropy behavior depending on this Q choice. So why is it so? Why we should use different than 1/2? So here is some calculation. So for each Q, we can find the stationary probability distribution of the states on this graph, and we can use entropy as average over the probability of being in given vertex times entropy produced from this vertex. And if doing so, we get this dependence from the Q. So this is a lesson that this naive choice that 1/2 is not always optimal. It optimizes entropy locally for one step, but not on average. And for example, in Ising model, going through some complex Ising model, we also will not use this standard random walk, but it's maximal entropy random walk. So here is some more sophisticated situation. So we have some graph which defines where we can jump. Like here is the simpler graph, but now we mark much larger graphs, and we need to find a stochastic matrix for this graph. And for each, it defines some stationary probability distribution, and you would like to find it to maximize this entropy production. So this is average entropy over the stationary probability of being in given vertex. And here is some situation, some lattice with defects, and so so there is a regular lattice. Defect means that you cannot. There are self loops, but these self loops are diminished, are removed. So without defect we have degree 5, and with defect we degree 4. So here are probability distributions for standard random walk. It's generic. Sorry, this is cut. As for standard random walk, so this is after 10 steps. This is some Gaussian. Around this is for this maximal entropy random walk, looks similar, but after 100 steps they start looking very different, and after 1000 steps they are completely different. So this is uniform distribution, and for maximal entropy random walk we get a strong localization, understand localization. Turns out we get exactly the quantum ground state stationary probability distribution using this maximizing entropy random walk. So here is some experimental data. So it's semiconductor, also this such defected lattice, and we look with a tunneling microscope what is the density of electrons. So we can see that it's not like this one, but like this one. It's strongly localized, and qualitatively, for example, for semiconductor, if putting electric field here, then electrons should flow. But here they cannot flow because they are prisoned in this entropic walls. Yeah. So this model of semiconductor would be wrong, because you would say that electron should be conductor, but it isn't. So there are these two philosophies. So standard random walk assumes that we have this drunken sailor, that he goes to the node and looks, sees three positions and throw a dice and goes according to this probability distribution. And in MERV, we assume that there is some, we take possible paths in this graph and assume uniform probability distribution or Boltzmann among them, and go. So MERV, we don't assume that the walker directly uses the probability distribution. Instead, it is us who use the model when we don't know what the walker does. So it's the safest, the maximizing entropy model for the hidden behavior of the walker. So these are completely different philosophies. So the walker doesn't use the MERV, only we use the MERV to get the safest assumption about the, let's say, probability distribution of finding the walker after some number of steps. Okay, so here are the formulas. So we have the graph given by adjacency matrix M. So for standard random walk, we would say that we should have 1 over degree. The probability each outgoing the edge is equally probable. For MERV, it's more complicated. We first need to find the dominant eigenvector of the adjacency matrix. So this is the dominant eigenequation, and then this is the stochastic matrix, and this is the stationary probability distribution. We can see the Born rule that we have to find the dominant eigenvector as for the largest lambda, and the lambda turns out to be minus energy. So maximal lambda means the ground state, the quantum ground state. So we get exactly the quantum ground state using this random walk, which is mathematically kind of this quantum mechanics after weak rotation. So it's not a surprise, but we get nice intuition where the squares come from here. So let us derive it to the Born rule, where the squares come from. So we have a graph, and we would like to assume uniform probability distribution among all the paths on the graph. So now the question is, taking such uniform probability distribution among paths, what is the probability of finding the particle in given position in this time? So here is the summation that we need to sum over y and z. So here is y, here is z. We perform t steps. So here is t steps and t steps here. And the question is, what is probability of finding x in the center in the limit t to infinity? So we perform this limit t to infinity, and in doing so, so there is this Frobenius-Perron theorem saying that there should be one dominant eigenvector. So finally, we get this one dominant eigenvector squared, because one psi comes from this left m, the second psi comes from this right m. So literally, one amplitude go from the left, the second amplitude goes from the right, and to get the probability, we need to multiply both amplitudes. That's the intuition for Born rule. The right for Ising model. Asking about probability in the center of Ising model, we get the Born rule to find the probability. Here is a more sophisticated, but I don't have time. But it's derivation for Boltzmann distribution. We have two ways to derive. One is, as I have shown, using this now and taking paths from minus infinity to plus infinity and asking what is the probability of going here. And this again is this derivation. We get the Born rule, we get the stochastic matrix. Second derivation is starting from now and taking paths toward future and taking ensemble of paths toward future and asking what is the probability of going the next step. So maybe here is a nicer picture that in standard random walk, going up or down, you look one step in future. So there is one step here, one step here. Now length 2 steps. So here is one step, length 2 steps here and 2 here. Then there's length 3, length 4, and so on. And in infinity, we get the maximal entropy random walk. So assuming ensemble of paths of infinite length toward future and asking what is the probability for the one step in such ensemble of paths. Okay, so it can be directly used for Ising model, for example. So there is this nice, there is this Markov field. There is nice Hammershelly-Clifford theorem that Gibbs fields like Ising model are also Markov fields. And Markov fields are this picture that the probability of the question mark under the condition of the blue values is in fact only depends only on the neighboring values, on the green values. Here is local Markov condition. Here is global Markov condition that the probability distribution of these question marks depends in fact only on these adjacent values. Or we can also do the scanning that the probability of question mark in fact depends on the value on this interface kind of, yes. So using MERV you can literally find the probability distribution, for example, this model, this scanning model. So we use MERV to get the probability distribution of pairs of such slices. Then we marginalize sum over the stars and get the probability distribution of this shape. And then we can get conditional probability distribution that having these values in the green positions, what is the probability of using the question mark here? Yes, and it works very nice for Ising model. You can get nearly accurate solution for Ising model. Here is the archive if somebody's interested. Okay, so now going back to Schrödinger equation. So in standard random walk, so here is the lattice I'm focusing now. So we have one-dimensional lattice with self loops, and some of self loops are removed. These are our defects. So a few self loops are removed, and here are the defects. It is one defect of length 1000 cycle, and here is second defect, third defect, and so on. So in standard random walk, what is the stationary probability of such length 1000 cycle with some defect? So standard random walk, the probability is proportional to degree of that. So this is 2 or 3 degrees. So this is so there is very weak localization, but strong localization. So here is logarithmic plot. So we can nearly all the walkers are in this zone. Yes. And to derive it, we have this eigen equation, subtracting, multiplying by -1, we get Schrödinger equation practically. It's discrete Schrödinger equation, and we say that this is literally the Schrödinger ground state density. Okay, so I also recently made working PN diode model. So can we do diffusion model for semiconductors? The simplest non-trivial is the diode, the PN junction, and it works literally. So here are some examples of density of electrons and the flows, local flows in PN junction. So here is NP as semiconductor with 2 types of defects, and the Ohm law is we get the nonlinear Ohm law that if we got this forward bias, then you get the conductance. If you have reverse bias, then you don't have. But then after some breakdown voltage, the conductance starts. So here it slowly starts, and here is very strong conductance. So we can get working diffusion conductance model of diode. So there is also nice. So there's a big question: should we use standard random walk or this maximal random walk? So for large object like for human walker, I would like to use standard random walk. But for example for neutrons, turns out that for neutrons they also observe this ground state. That so here is a line for neutrons. I don't remember details, but so here is for the standard random walk, and here is for the ground state. So and it turns out that experimentally for neutrons we should use diffusion, quantum mechanics, or diffusion according to this maximal entropy random walk. And here is the simplest difference. So having this 0-1 infinite well, the question is what probability distribution inside this 0-1 well should we expect? Standard diffusion would say that it should be uniform distribution, rho equal 1. Yes, but quantum mechanics say it should be sine square. Neutrons also say that it should be quantum. It should be like this one. And in MERV, we get the sine square because, so if taking ensemble of paths from now toward future, then you have first power, sine to first power. Or from now to the past, you have first power. But if using full paths, we get the Born rule, we get the square because one amplitude goes from the past, second goes from the future. Okay, now I can go to violation of the model like of Bell-like inequality. So so why people can try to hand wave about the original Bell or CHSH, there is this nice Mermis inequality which is much more difficult to hand wave around, let's say. So it says intuitively tossing 3 coins, at least 2 give the same. It's a completely obvious Dirichlet principle, one can say. And here is written as probability of that equal 2 coins are equal, 2 coins are equal, 2 coins are greater or equal than 1. So here is a derivation. Choosing any joint probability distribution, we have 8 possibilities. So this probability corresponds to these four situations. We sum all 3, and we get something like this. So whatever probability distribution, joint probability distribution you choose, it has to sum at least to 1 or above if there are no zero values. So we have used in this derivation Kolmogorov third axiom. The probability of alternative is sum of probabilities. Instead, if you replace it with the Born rule, you have the square, then here is example of choosing psi, which get the valuation to 3/10. So it's not above 1, it's 3/10. So it's much lower than possible. And in Ising model, we can realize it by using a sequence of 3 spins and with interaction which forbids this which enforces two zeros. So forbids 3 spins up and 3 spins down, and then as measurement is measuring 2 out of 3 spins, and doing so we should get this variation to 3/5. So it's not it's in space. So we get a stripe of spins, and we measure there, and the correlation should validate this Mermis inequality. So it's not in time as we would expect for standard Bell. It's in space variation. Okay, so in time, let's be 2 more minutes. So there are these a few quantum experiments. There is this Wheeler experiment that the question is that we can make the choice between classical and quantum after it was here is the aspects realization that the question is if it's classical or quantum depends on this splitter if you lift it or not, and so then it turns out that so if we lift it, it should be classical. If you put it down, it should be quantum. And turns out that the photon knew if we put it down or up before. So even if the choice was made after the photon goes to this beam split term. Okay, there is also this short algorithm which also kind of uses time symmetry, but I don't have time for that. There are many arguments for time symmetry. Okay, and let me finish because my time is up. So there is a way to perform field theories, classical and quantum, if we do it with the least action principle, with the Feynman path ensemble. So the least action principle is the one action optimized in the Feynman path, is Feynman ensemble among them, and in the center is kind of the Boltzmann path ensemble, the MERV I have talked about. Okay, thank you, and sorry for that.
You're welcome.
Okay, so the next, okay, Álvaro, yes, sure, you can share it.
Can you hear me?
Yes.
All right. Okay. I have to share a screen first. Okay, I'll share my screen, full screen share. Can you see my screen? Yes?
Yes.
All right. Okay, I'm going to put, this is a slide presentation. Okay, so you still see my screen?
Yes.
Okay, fine. So I'm going to connect 2 loopholes, which are the contextuality loophole and the correlation loophole, correlation in background fields. And I'm going to show how these 2 loopholes are related. And it's good. I think it's good news because if you close one of the 2, or you think one of the 2 is closed, the other one is closed as well. So this simplifies things. I will be very brief, but I want just to set the historical line, recall how all this started. And I want to recall the paper by Einstein, Podolsky, and Rosen in 1935, where they wanted to prove that quantum mechanics was not a complete theory. And for that purpose, they proposed an experiment to show that you could overcome the principle of uncertainty, which is the pillar of quantum mechanics. So they proposed an experiment with two entangled particles, the first and the second particle going through, you entangle them by letting them going through a double slit. And then you can measure the position of the first particle, which, assuming that is a local measurement, you are not affecting the second particle. And from the fact that these two particles are entangled and you know the difference between their distances, you can compute the distance of the second particle without intervening this particle at all. Let's do this experiment once again, but instead of measuring the position of the first particle, we measure the momentum of the first particle. And again, because we are not affecting the second particle and we know that they are entangled, we can compute the momentum of the second particle. So they said, I can compute the position and the momentum of the second particle without touching the second particle, and I have overcome the uncertainty principle. So if I assume that quantum mechanics is complete and then I can overcome the uncertainty principles, I run into a contradiction, and they conclude in their paper that quantum mechanics is not complete. And they only have to assume two things: that when you act on one particle, they are sufficiently far away, you do not affect the other locality. And they provide a definition of realism, which is here my main concern, which says that you can measure something is real if you can measure it without disturbing the system. So you can attack locality or realism in local realism, and I want to attack realism as defined by Einstein. But I was not the first who attacked their definition of realism, because Bohr in the same year, 1935, only 5 months later, he found a mistake in his reasoning, and what he introduced, apart from the principle of complementarity, which was introduced in this paper, he also introduced the concept. He did not say it explicitly, but he was introducing contextuality here. And what Bohr realized is that when you measure the position of the first particle, you have to use a slit that is attached to the same table. Then the particle goes through the slit, transfers some momentum in terms of electromagnetic radiation, but you can locate the particle because it's fixed. But when you measure the momentum of the first particle, you are doing a different experiment. It's a different context because the slit cannot be attached to the table, the same table, because you need the particle to transfer the momentum to the slit, and from this momentum transfer, you measure the momentum of the first particle, but you know the slit moves, and now the particle cannot be localized. This is the uncertainty principle. So there are two experimental contexts. And Bohr is very aware in this paper that you are not measuring something possessed by the particle. It's not that the property was possessed by the particle before. You are producing, through an interaction between the apparatus and the particle, the result of the experiment. So you don't measure, the properties are not real before measurement. You produce them, you create results through the measurement process. Okay. All right. But then, and I'm very happy with this, but then 30 years later, Bell, he was very inspired by the hidden variable theory proposed by David Bohm in 1952, which could explain the quantum theory perfectly, but had the property of being non-local. And then he thought that perhaps he could demonstrate that there is no local theory, classical theory, that can produce the results underlying theory, from which quantum mechanics would be an emergent theory, from which you can derive the results of quantum mechanics. And so if you renounce to locality, of course, you are just saying that there is an action in distance. So we have this terrible action in distance coming back, which was put by Newton in the first place with his Newtonian mechanics. And the idea is that when you measure one particle far away, some kilometers away, the other particle suddenly collapses. Okay, you cannot use this perhaps to transmit information, but there is an action distance in quantum mechanics. That's the idea. This has problems with relativity principle. At least it's not easy to think both of them at the same time. All right, so very briefly again, the idea, I want to talk about hidden variable theories. Perhaps you do not want to talk about it, but I want to talk because I think that quantum mechanics does not represent the apparatuses, neither the electromagnetic background fields. So there are hidden things, of course there are. And my point is that you can use these hidden things to explain them more stuff. So the idea of a hidden variable theory is just like the metaphor is thermodynamics. Boltzmann showed that you can obtain the results of thermodynamics from averages from the microscopic particles in the theory of Newtonian mechanics. So all the thermodynamic properties emerge from the averages by making just averages from the properties of the particles. So here is the same idea. Quantum mechanics is not fundamental. It's an emergent theory, and it's all its predictions in terms of averages and correlations and higher order moments must come from the hidden variables through statistical averaging. So in principle, it's a very clear idea, and it deserves attention. So to prove his theorem, Bell and also his advocates, well, Bell started using an experiment a little bit different from Einstein, Podolsky, and Rosen, and it's an experiment proposed by Bohm and Aronoff in 1957. And instead of position and momentum, they used the spin, the internal angular momentum of the particles. So the idea is that you have a beam of particles, you have a Stenger-Lach apparatuses with a non-uniform magnetic field, and then the particle interacts with the magnetic field, and then it can go up or it can go down. And so the experiment is just you have a source, you know all of you know the experiment very well. Let's say you have some pion zero particle, it integrates, and then you have two entangled particles through their spin. They are in an entangled quantum state, flying apart each other towards the respective Stenger-Lach apparatuses. You can orientate the Stenger-Lach apparatuses differently, and you can compute the correlations of the combined product of the spins of both particles in quantum mechanics, and you get these famous results. So the idea of Bell is that if you try to do this with some classical theory, underlying theory, you cannot explain these correlations. That's the whole idea. No? Okay, I'm going to use the last, the version of the theorem, which is the most modern one, which is the one which has the least number of assumptions, but there are some assumptions here, and I'm going to discuss if these assumptions are good for field theories. And my proposal is that so two of them are not completely correct, and you can modify them, but you must make assumptions to derive. The whole idea is that if you want to derive the CHS-H Bell inequality in field theories, you need to make further assumptions beyond these four. So, well, in principle, we assume that the hidden variables are whatever you want. Fields is the most complicated thing in classical theories you can think of. So dynamical fields, if you want. But then there is a function, there exists a function which is the result of measuring the spin. Here, Alice, if you want, measures the spin of one particle. And this function depends on some hidden data. And this hidden data, it's always believed that this data correspond to the source. And I'm going to show that you cannot only use in field theories data from the source. Okay, you have to put here the fields, the background fields all over the initial Cauchy surface. So this property, if you only refer to hidden variables at the source, is wrong. I mean, in field theories, you need more information from the background fields to propagate the initial conditions. And also, it is assumed that there exists a probability measure. Again, if you think that this probability measure does not involve the apparatuses, that only involve hidden variables at the source, you are wrong. You cannot obtain all the information from the particles. You need, because the background fields are playing an active role. They are contextual fields all the time, fueling the Zitterbewegung. Well, anyway, these two properties are the properties I'm concerned with. I will assume locality. I don't want to go into non-local stuff. I don't believe in axial distance. So basically, you can express the measurement of a spin by Alice without saying anything about the, just by specifying the orientation of the apparatus of that Stenger-Lach apparatus and not the other one. So both Stenger-Lach apparatus, you don't need to cross them here in the measurement of the spins. So there is no dependence on B here, no dependence on A here. I assume that's correct. So, okay, the theorem, the inequality of Closser, Horn, Shimony, and Holtz, basically is this inequality. You can use two different orientations for each Stenger-Lach apparatus and combine then the correlations to produce this inequality. This can be done as long as you assume this hidden variable integral. And these two statements are implied, each other implies. This was demonstrated in a paper in 1982 by Arthur Fine. He proves that if this holds, this holds. And if this holds, this holds. So this is necessary and sufficient condition. So if one of these two does not hold, then the other does not hold as well. And I want to show that the first one here does not hold unless you make assumptions on background fields. That's my point. Well, not my point, it's Morgan's point. I just connect this to contextuality. So quantum mechanics violates this inequality, and it is believed that classical field theories obey this integral, so you can, classical field theories cannot violate this inequality, but you have to make further assumptions. Okay, so the first thing, because I'm going to introduce contextuality, and people usually mix. This happens in some papers also of Marian. They mix times. So you have two different times, and you have to connect these times. The first time is the time of measurement, if you want, or that's the second time, the latest time. That's when you measure correlations. Correlations are not measured in the beginning. It's just when the particles arrive at the apparatus. So strictly speaking, your correlation function must be computed with the probability density at the time of measurement. And the hidden variables appearing there is the particles hidden variables, and also the apparatuses hidden variables, because you have the magnetic field of the Stenger-like apparatuses, but that's at the time of measurement. So what you have is a probability density evolving in a space-time, which you have a stochastic process if you want, and you have a measure on a set of events. And moreover, this probability density at the time of measurement is contextual. It depends at the time of measurement on the apparatuses. Because if you change the orientation of one of the two Stenger-like apparatuses, this probability density is going to change. The interaction between the particle and the apparatus is different. All right. So you cannot avoid here in this, at the time of measurement, I insist, the dependence in the probability density of the orientation of the apparatuses. So now the question is, can we go back to the source and forget about this dependence, about putting in the probability density this orientation of the apparatuses? And you can if you make certain assumptions. Okay, first I'm going to show that in a Newtonian-like theory, which is what everybody has in mind. I mean, people don't worry about fields very, very often. So if you don't worry about fields and you think that properties are coded in the particles, if you really assume that, you can do the inversion. You just have a Newtonian-like theory. The spin is possessed, a property possessed by the particle, if you want, from the very beginning. You don't need contextual fields. And in that case, you just need the flow. You have some initial conditions in position of momentum or spin, whatever, in the particles of the hidden variables. You evolve them through like in differential geometry by a flow, and then you obtain the hidden variables at the time of measurement. So you can backward propagate the flow, and you make a change of variables in the hidden variables through this integral, and you obtain the desired integral correlation with the one which allows you to derive CHS Bell inequality, or, well, with another assumption, Bell inequality, original Bell as well. But when you put fields, things are different. And I will show in what sense. So this is, again, the integral at the time of measurement. This is the fields in some region where the particle rests. I mean, you can assume that particles are extended objects, or if you want points, you can assume they are points, but I put some functional integrals because I can assume some very little region where the particle is. And here I have the fields, right at the time of measurement still. And of course, you have a dependence on the orientation at the time of measurement. And now in partial differential equations, because you have to take into account the evolution of the fields, the contextual fields. So if you want to find out the fields of the particle here, you need to specify at the beginning, when you set the source, all the fields in the causal past light cone in the Cauchy surface. Okay, I'm going to suppose a linear theory just for simplicity, because you can use a Green's function and you have a propagator, but you don't need it. You only need to use Cauchy-Kovalevskaya theorem of uniqueness and existence of solutions, and it is guaranteed that if you have this initial data in this past light cone at the beginning, then you can obtain the value of the fields at the time of measurement. Okay. So let's see if we can backward propagate to the source now and what happens. So when you do that, the problem is, okay, forget about the gray region. You have Alice, This is where the particle is measured inside the Stern-Gerlach apparatus. This is where Bob measures the spin inside, if you want the other Stern-Gerlach apparatuses. These are the world lines of the particles. This is the source where they are emitted, but you need all the information to obtain the result in the entire causal past cone at time zero, where the particles are created at the source. And the problem is that now that the apparatuses are inside these light cones, okay? So in principle, when you revert the flow to get the initial data, you cannot avoid a dependence on A and B, not for the moment. We will discuss if you can avoid it or not. But in principle, you cannot avoid it because you have the apparatus here, all right? And these fields, it's not just the apparatus, it's the fields in between the apparatus and the source. There are fields, background fields fluctuations all over in the entire, so you need these fluctuations. They are traveling through the electrovacuum. Okay. So in which case can you neglect or avoid this dependence? So here is what you need to assume: two things. And these two things are explained in a very amazing, brilliant, I think this is a very brilliant paper. It's not very cited because people in Bell world, they don't really care in general about fields as far as I have read. Not truly care about fields, all the details of fields. But this guy really cared about it. And he said that there was an enclosed loophole. He called the correlation loophole. What he's saying is, if you want to go from this probability density, define all over the past causal past initial data, initial hidden field data, you need further assumptions. So let me be brief and concise. This is the past cone, the red region of Alice. This is the past cone of Bob in the initial data. I'm going to define the intersection where the source is between both initial past light cones, and I'm going to call this sigma C. I'm going to define the region of the past light cone of Alice that does not intersect with the past light cone of Bob as sigma A. And I'm going to define by the same rule, this region sigma B, where you have all the initial fields except the intersection with Alice. And you have these three regions, this region for Alice, this region for both, and this region for Bob. So in this case, if you assume, you have to assume two things. I think one of them is quite reasonable. And the other one, it must be proved, and it's not easy to prove at all. You must assume that the probability density, or if you want the fields here, all over the region sigma A are uncorrelated to all the fields in region sigma B. And if you guarantee this, you can separate both. And then if you also assume that the probability density of where the source is does not depend on A and B, which is very reasonable, I think, because otherwise you would get a superdeterminism in the original sense of Bell. I will say some more words now. If you assume this, if this holds, you can derive the CHS-H-Bell theorem. But if you don't have uncorrelated fields here and here, or here and here, you have to prove that all over this region and all over the region they are uncorrelated. You cannot derive the CHS-H-Bell theorem. And some people would say, well, this is some other kind of superdeterminism. In some sense, you could say yes, but it's not the original one. I'm not saying that the fields of the source are correlated with the orientation of the apparatuses. No, it's not the fields of the source. It is the fields outside in this light cone in sigma A and sigma B, and that's different. If you want to call that some kind of revised superdeterminism, okay, I think it's a misnomer, because I'm going to show you that you don't need determinism at all. And if you don't need determinism, it would be quite weird that you need superdeterminism, but I don't like this word anyway. But okay, because if you are deterministic, you don't have to worry about superdeterministic. But whatever, I understand. I would call this conspiracy. That's how it was called also by Bell, and how Morgan calls it. This does not depend on A and B. This I can assume quite good, but that these are uncorrelated, that's saying too much. It doesn't hold in quantum electrodynamics. And I don't think it holds easily, but you have to prove it experimentally. It's a loophole. And it's connected to the contextual loophole. I've shown that. It's just Green's function connecting both of them. Okay. So if you want to assume that your apparatuses are dynamical and you set them in flight, last instant choices, and you want to assume randomness, whatever, it's the same story. If you want to put randomness, okay, you put some Langevin current here in your, and you get a stochastic partial differential equation. You have a Langevin force, and you have just stochastic fields. Yeah, okay, that's fine, but still, you have the same problem. And the problem is that when you put the apparatus A and the apparatus B, even if you did last instant random choice, when you compute the correlation integral for these two values, A and B, you are choosing from the initial hidden data in the Cauchy surface a part of the whole ensemble of the sample space. You are selecting, you are restricting your original sample space to this situation. So it's going to appear A and B here, and the same problem is gonna be here. So you can use also stochastic field theories. I don't mind. The mustache of Langevin is bigger than the mustache of Aspect, and I can cover also stochastic field theories. Doesn't matter. You have the same problem. You need to guarantee. In fact, Morgan paper is about random fields, but I don't believe in randomness. I come from chaos theory, so I think randomness is a redundant concept for me. Anyway, how do you close this loophole? Well, well, in principle, you just have to measure all the background fluctuations in this region. If you have photon experiments at Aspect, I mean, I would see very, very hard to close the loophole, because all the background field fluctuations here, you have to measure them somehow and prove that they are uncorrelated to the background field fluctuations. And these regions, you know, photons travel at the speed of light, so it's the fastest you can go. So the intersection region is just going to be the photons. So these fields will be correlated with these ones. So I don't think experiments with photons are very good to close the correlation loophole, but I don't know, perhaps some experimentalists has better ideas than I do. But from the theoretical diagrams, space-time diagrams, I cannot tell. This is a really good setting. I would use instead to try to better close this loophole, also, although you still would have to measure background fluctuations. Fermions, like I showed before, the EPRB experiment, and they would have to be relativistic electrons at half the speed of light, above. So this region is maximized. And in this way, you avoid the problem of having correlations between this region and this region. If this is 3 kilometers away, it would be hard for me to assume that this is correlated, the background fluctuations, with these. Anyway, if you want to be rigorous, you would have to prove that this isn't correlated with this. So the loophole would persist, although I would be quite satisfied if you proved in this kind of experiment with fermions have the speed of light, that there are violations of the Bell inequalities. But it's really, really hard to measure background fluctuations. There are experiments. I found some beautiful experiments here. There's an experiment to measure background, but you have to use lots of apparatuses, and you are going to distort the background fields quite a lot. I don't know if you put here an experiment to measure the background fields, you are going to destroy entanglement, in my opinion. But I don't know. That's it's not easy to close this loophole, as I see it, at least. So finally, to conclude I will say a few words on how I see, from a reasonable perspective, what entanglement can be. And well, in other talks, I've shown that how extended electromagnetic objects can have Zitterbewegung. I have also shown in other papers that perhaps background fluctuations are also required to sustain this oscillation. It's a very nonlinear oscillation. It is called self-oscillation. And I have derived it from the memory in Liénard-Becker potentials in classical field theories. So it is very well known in the world of nonlinear dynamics that if you have two nonlinear oscillators and you couple them, and here you have a background field that allows to couple them, they can synchronize. So you have two particles, and they can synchronize in synchrony. And if this happens, whenever you measure one, the other can be anti-correlated with the other. This can happen if there is synchronization. So why do I think that background fields are important? The reason why I want to say this is because if the background fields are totally uncorrelated, it is quite likely that these particles are going to lose their synchrony, and then you are going to produce a decoherence of the entangled state. So my point of view of entanglement is that entanglement is just synchronization. It's a nonlinear dynamical phenomenon coming from the oscillation of the particles. And this was already found in clocks by Christian Huygens in the 17th century. And that's the only way I can picture. Of course, perhaps we don't need to picture, but I still think there is something there. Finally, I would like also to say a few words about Zitterbewegung, because I used Maxwell theory to derive self-oscillation, but in a more fundamental theory, particles must come from fields. And you know, if you want to have, when the two particles start at the source, they leave the source and they are, their spin, their angular momentum internal must be oscillating very, very dramatically. And it must be because I think the shape, even the shape, it's not just that particles are extended, their shape is evolving. Because if their shape does not change, you cannot get two options, up and down spin. To get two options, you need that the shape of the particle changes. If you have a rigid magnet, you have, if you put a field, then you have only one stable direction and one that is unstable. But if you get both attractors as possibilities in a dynamical system, that means that the shape of the particle must be changing. So I think the particles are oscillons, and that these oscillons are producing background radiation. And this, well, I found this beautiful paper I read a week ago about oscillons and quasi-breathers. So perhaps you people are very interested in soliton models. Perhaps oscillons and quasi-breathers can produce this ether. And I think also it depends on background fluctuations anyway. I don't know really how in this case, because I don't know if an oscillon can absorb fluctuations from the environment, but there is an interaction with the environment. So my conclusions is that quantum mechanics is incomplete. And the reason is that it does not represent contextual electromagnetic fields, fluctuations, and it does not represent the apparatuses. Quantum electrodynamics, which is much better theory than quantum mechanics, does represent the background fields, but not the apparatuses, so it's still incomplete. And my conclusion, this is Henry Casimir, is that because there are background fluctuations in the context, is that local classical field theories do not comply with the principle of local realism, because they are contextual. The particles are interacting with their environment. They are not isolated particles traveling in nothingness. They are going through the vacuum, and the vacuum is alive. So particles are dissipative dynamical structures interacting with their environment. No isolation, that was already said by Marc Fleury, and that's my point of view, and that's all that I had to say, and half an hour.
Thank you very much. Any quick questions, comments? I'm skeptical, but that with Euler-Lagrange you can get violation, but
I have a few comments for Álvaro. First of all, wonderful talk. Then you showed the Aspect schematics with just two detectors and claimed there was randomness in there. If you recall, in my presentation, I showed that technically speaking, they never really have that, in-flight setting of the measure that Bell prescribed. They have a choice on 4 static measures. So I would love to, to hear include that fact in your thinking, the isolation, the 4 measures are there. And I would love to see a mechanism by which, whether contextual, you seem to be thinking a lot about that. What would be the mechanism for these photons since they see the 4 target? Is it something at the source because they see the 4 targets? Is it something evolving like a Stern-Gerlach where the output is a dynamical interaction? I don't know. The second thing I want to inject in your thinking, sorry, just to put it all in, is, in my own experiment, I do remove the synchronization. It's intermittent. Yes, in that, the one before. Yes. In that analogy, I love that analogy. This is something like that is going on. But I also want to inject into your thinking that in my experiment, I think I proved that it has to be an intermittent, my signal is intermittent, so it cannot be an instantaneous or a traveling wave. It has to be something averaged. It has really to, it has to be an average field. That's it.
Okay. Okay. I must confess I have printed your paper, but I have not arrived at it yet. But I will read it and I will contact you and tell you about how I can rethink these ideas in relation to your experiment.
Me encantaría hablarte directamente.
Un placer, lo haremos, palabra.
Vale, muy bien.
Álvaro, I wrote some remarks in the chat. I think you misrepresent Bell, and I think you are bringing in a non-locality loophole because you're allowing Alice's setting introduced at the very last moment to have immediate influence on Bob's outcome. Yeah, yes, that's what I think. But I mean, we can discuss this. But certainly, I want to say that what you say about Bell's assumptions are definitely wrong. Bell did not assume the kind of things you claim he assumes about lambda. That lambda of Bell may be very, very, very non-local. It may be all over the whole universe. It's the situation of all the fields sometime before the experiment starts. And then, of course, it can evolve in time. The assumption of Bell, at least the local hidden variables assumption, which is the question whether or not it's true, is that the settings A and B can be inserted at the last moment.
Yeah.
And that's what the experiments do.
But the problem is that you need to. What is the orientation of the apparatus, Richard?
It doesn't matter.
It's fields. And you have to backward propagate those fields. This is the integral. And when you backward propagate those fields, you are restricting the initial set of hidden data to a sub-ensemble.
No, you can't. Point I was trying to make.
No, it's pure statistics.
So you're believing in retrocausality.
No,
stop. This drawing
and the fields earlier are different. Okay.
This drawing from Aspect is misleading. We do not have we have dynamical switching, but we do not have dynamical setting. Okay, anyway. And you are wrong, Richard, when you say it is not important the orientation of the polarizers. The polarizers,
of course, it's important. I did not
exactly.
Say
Thank you. They're always
seen, wait.
They're always seen by the source. The polarizers are completely known at all times, statically.
Yes, that's not
by
the
source.
Just
something else is and Zeilinger. And
okay, just a few words.
So convoluted,
I want to respond, Richard, assuming that the experiment is as he says. So let's assume that he's right, and they choose it. I have assumed that. The point is that when you are selecting, I mean, you have to backward propagate to initial conditions, and the initial fields here. Okay, if you are selecting all the cases where you obtain A and B instead of A prime and B prime, for instance, then you are also making a restriction in the sample space of the initial hidden fields. And this is why you cannot, oh, you disagree? So you are telling me, no, okay. Because, no, the whole sample space is the whole set of fields in all the cases. And if you make a selection in this
you are not
space
making a selection.
You are, yes, of course you are, because here, I'm doing it here.
Okay,
yes,
we disagree.
That's because you do not understand field theories. Because when you backward propagate the flow of a field theory, you are restricting it. You are not going to get all the
you're talking about retrocausality.
Okay, I will say you don't understand field theories. You don't understand field theories. If you think that when you put here, you have not understand the argument because it's contextuality produces the argument. Yes. Look. If you set here A prime, then you are selecting a different sub-ensemble of the sample initial space. So you get here A prime and B prime. Well, okay. So you are saying that if you get the sample space, you are a statistic.
If you say that,
no. Okay, you are a statistical man. If you're a statistical man, if the whole sample space of all the fields is restricted, you must get something that denotes this restriction, and this is A and B.
Yeah, that's retrocausality. You are assuming retrocausality.
No, it's not retrocausality, for God's sake. It's, okay, whatever.
Why not?
Whatever.
Okay, so maybe you can take the discussion to the chat.
I'm not against
retrocausality. Field theory, Richard. Study field theory.
It's static. It doesn't come from the future. It's static.
I study statistics. I teach stochastic processes. I tell you this.
Talk some more.
Okay, study fields, please.
Okay, so Robert,
no idea about fields.
You can continue at the end. So at the end there will be a lot of time for discussion.
Yeah, it's okay. I'm sorry. I get excited. Forgive me.
Robert, could you share? Could
I
you
got it
stop?
one here.
Yes, yes. Sorry for the delay.
Okay, get in slideshow mode here. All right, can you all see that?
Yes.
All right, let's use that little thing there. Okay, so I'm going off on a completely different line of thought here. Just looking at simple geometry and the actual Bell theorem itself, and I'm not going to talk about experiments at all. So, let's see, can you all see that? Because I'm kind of blocked here. So, well, you all know about the EPR paradox. I'll just skip that one. So, the basic problem is that there's this appearance from the experiments that it looks like making a measurement on one particle seems to affect the other particle. And so that's why it's called a paradox. And as a lot of you have been saying, that makes it look like physics is non-local. Okay, but I'm going to give an alternative explanation. And what I want to do is look carefully at Bell's theorem, the way he actually derived it in the first place. So he says you've got this two-particle correlation, and it's the sum of the product of the measurement at A and the measurement at B, right? And those are binary, plus or minus 1. So the theoretical value for this correlation over many experiments is you have some density of states, then you multiply the two measurements together and you do this integral over all the different states. And then he looks at the, well, first of all, he says, well, suppose measurement at B is minus measurement at A. This is for spin correlations. He says, look at the difference between these two correlation functions and writes it out. This is A and B, this is A and C. Then he factors out the A part. So you get this product of the A and B measurements, and then you have 1 minus the product of the B and C measurements. And then he says, because the maximum is 1, you can state this inequality here. Nothing controversial there, I think. But then the last step is he says that this term here is the correlation between B and C. And it's this last step that I claim is incorrect. And I'll just give you a simple example of why that's incorrect. So suppose you have a spherical surface and one hemisphere is +1, the other hemisphere is -1. And the picture I have, I think I have on the next slide here. So the theta equals 0 at the top here, and you're measuring theta this way. So that's theta A. And the division of plus and minus is along a circle where the azimuthal angle phi is constant, could be 0. And in that case, the measurement at angle A for given azimuthal angle, I call it phi, some people call it phi. And, it's just the sine of sine theta A sine phi. Okay, very simple. And then the catch here is that your density of states you have to define in terms of the angles. So the solid angle you can write as magnitude sine theta A d theta A d phi. But notice that you could also, if you're looking at the measurement B, you could define the solid angle as sine theta B d theta B d phi. So there's different ways of defining the solid angle, for determining the density of states. Okay, so let's just assume that entanglement amounts to fixing the azimuthal angle. And then your measurements A and B are equal and opposite. So you've got like basically two copies of the sphere. They go off in different directions. One of them you measure at angle A, the other you measure at angle B. And the one you measure at B is inverted for whatever reason. Maybe because it's traveling the opposite direction. Okay, so once you've picked your angle A, and then you've also picked your angle B. So once you've chosen your angle A, the position of B is completely determined. You just add the difference between those two angles. So you can either pick any description of the solid angle that you want. You can use theta A for your solid angle, or you can use theta B to define your solid angle. Okay, but once you've done that, so if you say the probability for A is in terms of solid angle A, the probability of B given A is just 1 because it's completely determined from the angle between the two measurement locations. So the joint probability of A and B, again, you can either write it in terms of the solid angle relative to theta A, or you can write it in terms of the solid angle relative to theta B. Either of those is valid. Okay. Okay, so for equal solid angle, that's a definition of density of states, but of course the parameterizations are different. This d theta A and d theta B are in general different because they depend on which angle you're looking at. So when you get to Bell's theorem and you're looking at these two different correlation calculations, when you get over to this one, so these are all calculated. You can use either theta A or you can use theta B. And this one you can use theta A or theta C. But in any case, both of these you can use theta A. But if you're using theta A here, then you're not matching the density of states with the angles that you're actually measuring. So this last step is not the same as the probability of the joint correlation between B and C, because you can't, neither of these angles corresponds to theta A, which you have to use for both of these. Okay, so this last term is not the same as P of B and C. Okay, and then just to give a little calculation, just to show that this is legit, I said that for my hemisphere, the measurement at A, you can write as the sine of sine theta A sine phi. The measurement at B would then be the sine of sine theta B sine phi. And if you work out the correlation, you've got this integral where you're multiplying these two things together, and then you're dividing by, essentially the total solid angle to normalize it. And the result, when you do that calculation, the result is minus cosine theta AB. I just did it numerically. You get exactly the cosine correlation. So the same as what you would get for spin measurements. That, of course, leaves open the question of what exactly is a spin measurement, or what exactly are photon measurements, and I don't have an answer for that. But just in terms of the theorem, it's very clear that which step, in my view, is wrong in the theorem is calling this thing here P of B and C is not correct. And that's just plugging in the numbers there. So, okay, so my summary is that Bell's theorem does not apply to rotational systems, which is what I just did, because the expression for density of states is different for different angles. And if you look at other non-commuting variables, for example, position and momentum, momentum is essentially the Fourier component. And if you're calculating things in space with the differential volume dx, dy, dz, that's different than calculating things in the Fourier domain, where you have dkx, dky, dkz. So if you're using dx, dy, dz, you can't suddenly plug in a Fourier component and try to calculate something with Fourier components. You're stuck in either one domain or the other. I'm not able to prove this or anything, but it seems to me that this inability to define a single density of states seems to be a general property of non-commuting variables, which are what Bell's theorem addresses, or at least the EPR paradox addresses. Okay, so that's the end of my talk.
Thank you. So there is a lot of time. So the problem is there are some questions, comments, especially from Richard.
I have a question. I think I made some remarks. Robert, I think you were looking at like Bell's very first try, and things changed a lot since then. And I was very proud that in 2001, I wrote a paper in which I showed how to take care of things changing as time goes by using a statistical technique called randomization, which physicists don't seem to know about, but the rest of science does. And I proved a different Bell's theorem. I make a bit stronger assumptions. I make slightly different assumptions. I don't assume a constant probability density of lambda. I assume that settings are chosen at random again and again. That's the randomness. And I prove a Bell's theorem. And it was used in the experiments in 2015. So this is another example of what was it, flogging a dead horse. I mean, things have changed. The newest experiments are very, very different. And people are still picking holes in Bell's original proposals and work. And he saw the holes too. He spent his whole remaining life fixing the problems, and his theory grew and changed and evolved and got better and better. And that went on after he died as well. And it's still going on today. So that's kind of my summary of what I think to what Mark is saying and
say
what
that
Robert
the tech
is
has
saying.
evolved, but actually the tech.
Yes, it can be interesting, but please catch up.
The electro-optic modulators are all the same. They still do that. By the way, it's weird that.
Yes, so what?
Well, so you would never have isolation.
No, hold it. When you do an experiment with neutron, with nitrogen vacancy defects.
Time out. I have run these claims by Gregor Weiss. Gregor's thesis.
Yes, I know. That was 30 years ago.
Gregor is still involved with the modern experiments.
I know, I'm still involved with him.
It's still the same components. It's still the same.
They still have some of the same components, and some of the experiments are getting rather different.
Stop, Richard. We do not to this day set the settings of the polarizer. That's just not true. Stop saying that.
I'm not saying that you do.
A real Bell test.
Experiments with
We're not doing a real Bell
nitrogen.
test. Bell wanted us to set the settings in flight. We don't have the tech to do that. Stop saying the contrary.
We don't do the experiments the same way at all now. The photons now go from Alice and Bob to Charlie.
It's the same components, Richard. The
No, it
components
isn't.
haven't changed. No, sir.
No, it isn't.
No, sir. No, sir. I do the
No, sir.
experiment.
No, sir. When you measure the spin of an electron
Oh,
in a
but
nitrogen
that's stuff. I just don't. I mean,
defects
if
in
I read those
diamonds,
papers,
you are
there's
not
layers
doing the
and
same
layers
thing.
and diamonds on top of photons. I don't know what the heck is going on. I don't
Well, I
even
think you
try.
should have a look.
I have
I'm
had
just
to look. I
suggesting
don't
you take a
understand
look.
these papers. I don't try to understand these papers. They're too much. I'm
Well,
not a
they're not.
professional. I'm here to
But
understand.
even I can understand them a bit.
Well, I try. Well, you say that, but anybody who
Yeah.
claims he has
Well, I can
understood quantum
understand-
mechanics does not
I
understand.
can understand the scheme of the experiment,
Somebody.
and it is totally different from
No,
Weiss's
no, no,
experiments
no.
of whenever.
The photonic experiments use exactly the same EOM
They
components.
use some of the same
No, no,
components, and they
exactly.
are
Look at the schematics.
totally
I put it
different.
on my slide. Look at the schematics of the Malta experiment recently. Look at, I mean, it's all
Of
the
which
same
experiment?
EOM. It's the same EOM, Richard.
Which experiment?
The
Hey,
one with the
guys.
submarine fiber. Submarine
Guys,
fiber.
can I ask Richard a question?
I think you should have a look at the latest Munich experiments.
Oh God, whatever.
Or Robert, I mean, can I ask Robert a question?
Sure.
Since this was his talk, I'm curious. Going back to the actual original theorem, I think that Richard's point is quite relevant. But the thing that I'm interested in is that your overall point seems to be that, and I may not understand, but it seems to be relevant to the question that I asked originally, which has to do with probabilistic compatibility. And it seems to be that what you're saying is that you can't collect all of these correlations in a single density function. And I may be wrong, and that's what I'm curious about, because the thing that I find interesting about probabilistic incompatibility is that it seems to have been discovered independently by many people. And if that's the case here, it's another instance of that. And then I think that you would be interested in the literature on that subject if you don't know it.
Yeah, actually, I probably would be interested, but yeah, this is just a basic, how do you say, observation that, you know, when you choose a density of states, which Bell does in his original theorem, you have to describe that mathematically somehow. And when you do that, you pick, in this case, some parameterization. And once you pick that parameterization, you have to stick with those variables. And if you pick theta A, you can't then use that when you're not using the angle theta A, basically.
Yeah, it seems similar, and I have to dig into it a little bit more to really understand. But it does seem similar, so I can try to send you some of these papers, and then that would be really cool if this is just another case of another person independently discovering this same idea that has happened multiple times.
Okay, yeah, I mean, it's a very simple example. You know, this sphere with the two measurements on it. It's a very simple example. And to me, I think it gets to the heart of Bell's theorem, although, like I said, I have no idea how that relates to actual experiments.
Yeah, and as Richard says, there are lots of different versions now. And so it will be interesting to try to distill this and see if it applies to the later theorems, the later versions of things.
Yeah, I think there may also be some connection with what Jarek was talking about with the Born rule. Again, you have to look at what are the probability densities that are associated with the variables that you're measuring. But I will add that I think it's crucial that this applies to non-commuting variables. You know, you wouldn't have the same problem, I think, if the variable is commuted. So.
I mean,
Thank you very much. Should we move on to the next speaker then? Jim?
Yes, but another 3 minutes, so we can actually have some discussion. I don't know, or you can start earlier as you want.
All right, I'll stop
Okay, move on then. Okay, let me present. Oh, and I should have practiced this ahead of time. I need to allow my app to share. This is anybody know on an Apple how to allow my system to share? I always get caught with that. I go to present and I can't do it. Or I mean, I that's Apple Library. It says, as I try to share, I'll need
Which
this
app
3
is
minutes
it? Maybe
just
I
to
can
share.
Google it while you try.
Yeah, or
Which
ask ChatGPT. I'm on a Mac and I'm on Zoom. It looks like I'm on the app of Zoom, and I went to hit share, and it told me, I picked what I want, and it said, try it one more time, share sound, doesn't really matter. Optimize for video clip might be good because I've got a visual demo. Open system preferences, go to security, privacy, and grant access. So system privacy, grant access. How do I do that? Looks like I need to find Zoom. I apologize for this. Try to talk while we're doing this. Why? Okay, Zoom, here it is. I got it. I'm 5 seconds away.
We started early, so you have extra time.
Okay. All right. I think I can Zoom now. I believe that it's going to work. Yes. And I'm a computer programmer. I should be better at this stuff, but embarrassing. I just presented to my whole company. First time CEO saw me and my computer locked up, and I'm like, oh, this is great. You probably think I'm incompetent. All right. First of all, I apologize. I tried to listen, but I also wanted to do a good presentation. I put together pieces of this while this was on. This part I just put together. I've been working for quite a long time building the rest of the stuff, though. And just as a quick preview, this is what I'm going to show you, something that Richard Gill spent some time looking at and saying, add this, add some seeded generators out with the output, and really appreciate his help. And then like, okay, prove to me that these particles are not communicating with each other. And I'm like, it's in the JavaScript. And Jill said, I don't read JavaScript. So let me show you what we got though. But appreciate very much everything. And the names I saw here, just some of these people I've read in these magazines, I'm like, wow, Bush on his, amazing. Okay. Thank you, Chantal, for putting this together. Incredible. I love working there. Just discovered her blog. It's really cool. So why does a computer scientist something interesting? I beat the hell out of this data and tried to figure out what's going on. Because early in my career, as a high school student, I learned relativity and this makes sense. And I started, I came up with a Gedenken something where it's like, okay, some questions like, does the universe, I have an idea about, is there a universal, I don't want to go off the topic, but is there a reference frame through your rotation that is universal? And does that work with relativity? Apparently it does, but I came up with the same thing that I'll mention something, but there was Isaac Newton had this idea of rotating buckets. I'd come up with the same idea. It's like, oh, he already did that. Yeah. Anyway, so I created a little site where I've got, some of these ideas. But the biggest thing is when I found out EPR is supposed to be wrong, I said, no way. It offends my senses of, does this really work? So I had to prove it to myself. I had to write a computer program, and long story short, found out it's really easy to violate Bell's inequalities. If you're writing a test, you're getting a violation. I don't believe it. It's like there are so many ways that you can. It's just like it says violated because a computer is the math right? I heard people saying it wasn't. So I proved it, and I know the math is right because I can simulate exactly what's happening. This is the quantum theory where it has no properties, hits something, and the math comes out. I'm going to put this in fast mode. It's slow so you can see it, but it just everything they said it was supposed to do. It's 2.8. It comes right there, and a lot of the math I was like, oh, this is probably a cosine thing, and then later Bertelsmann socks. Thank you, Gill. It's like, oh yeah, this is something I can understand. And then I went back and was with these guys. What's going on? What sort of ways can it be faked? And as I understood, and I've got a I did early on. The main thing I'm focused on is control tests and saying, why do we want to do control tests? What's the argument for that? Oh, that's so over here on my actual test, here we go. So here, this is a paper on it. And I started seeing these patterns and was like, okay, where does it have to, and it was mostly started with loss, but later rotation. What particles cause violations, what don't? And found out, okay, when the particle hits the deflector, and I'm thinking in the terms of, classical particles, these have properties. So, because that's my mindset. So, okay, if it is classical, by the time it hits the particle, if it's exactly aligned or opposed that particle to the deflector, and then it goes and gets hit, wow, there's a strong violation. So either by losing ones that aren't, or by rotating things to match it, we get the strong violation. So like, and then Chantal Ross said, wow, that looks like Malus law. And you know what? When you go through a deflector, it gets rid of, you get lost on just the ones that are not well aligned with that deflector. It's like, wow, it's inherently flawed. And so what do? We can start coming up with ideas. But the main thing we came up with is we can actually do control tests and find out if there's inherent flaws, simple ones, not exotic loopholes, but simple things. We can say, hey, I can make this experiment and like, okay, are we really doing this right? Are we thinking right? Chantal literally yesterday asked ChatGPT and got the answer back from ChatGPT and said, oh yeah, that's been proposed. Here's evidence and here's how to do a control test for negative, for positive. You can show that your experiment is capable of violating and capable of not violating with control tests. So without going, maybe I'll just jump to that because that's where I've been spending my time. I was going to go back and add more, and I'll show you a little bit on this presentation put over, but I'll show you a little bit with this diagram. And some of the stuff Gill said is, okay, give me seeded, advanced random numbers so that I can recreate it and let me dump the data, this export button, and it dumps it out. But the main thing is I have this one, and I'm going to rename these. Real Perfect's going to be called Classic Model. And what it does is it just models what Classic can do and make this slow so you can see it. So it just does what Einstein said it would do. These particles already have polarizations, they hit the deflectors and they go one way or another, and we get all, and I speed this up and let us see what the actual numbers are. And, you'll see, yeah, it's not violating. It's like a 1.4 or something. There's no violation. We added some Eberhardt, and I think some of my Eberhardt was correct, some needs some work. And another mode I was going to do is, which I haven't done yet, and then we have ones like we can simulate, violations with loss. And the other one that I need to add is where you do the exact same as loss, only just rotate the polarization so that it gets the same numbers, and we'll get the same. It'll equivalently end up with, depending on how much you rotate it, you completely rotate it to exactly violate, you're going to get the 2.4. If you do just partial violations like quarter plates where you can change polarizations without loss, then you'd get something in between. So I'm coming back to that, and I'll update my papers. But basically, so the main thing is, it's like everybody, there's always a loophole, no loophole. Everybody tries new experiments. There's people like Mark Payne who helped me understand this early and said he looked at the data in detail and found, possible issues. But I don't want to have to do all that work. Can we just, design control tests and say, let the experimenters do what ChatGPT, that's this great API. If you haven't seen it, it does not repeat what's on the web. It learns the web, learns concepts, and returns those concepts back to you. And it is absolutely amazing. So literally, I can put my code into it and say, I'm getting this weird error. What's going on? It'll say, oh, it looks like you messed this part up, and it'll rewrite it for you. Unbelievable. The singularity's coming, people. All right, so here's the control test. And I would hope to eventually get this. I've been wearing the small group for a few weeks now. I haven't bothered Gill with it yet because I want to get it clean before I waste your time. But we think we're getting close. And I especially like when I got that feedback from ChatGPT that said, oh yeah, and it was so close, but so much more clear than what I did. So this is kind of what I wrote. And there was a great movie called Fargo. How do you know? So a nice quote. So with the computer simulations, I learned a lot of stuff, figured out how easy it is to violate stuff. And how am I doing on time? I'm only 5 minutes in. Wow. Yeah, thought I was running out of time. Okay, so here's the criteria. It's basically, you got an experiment. It's possible to fake a violation and it's possible to not have a violation. If you, so accept that part, that you can, any experiment, if you just, before the experiment starts, you don't touch the experiment, you don't change, but just at the emitter, if you have three ways to do it. One, the standard experiment, you admit particles, all you know is that they're entangled. But then you can also say, for a control test, I can say at the emitter, I'm going to let you have full knowledge of the application actually in the violating mode. If you want to do quantum, I'm going to let you pre-correlate, and just so I can prove that, hey, I can violate. This is a violate, and this is a test that's only needed if you want to prove Einstein, which is good. So if you want to prove quantum, a much simpler test. All you have to do is your test violates. That happens all the time. You know it can violate, but do a control test that says prove this possible, not violate. Show me that you're not rotating those angles or doing something with your waves or something, so that when it hits the deflector, it's already biased to give me the answer that you're looking for. So the way to do that, if your test is truly unbiased, and maybe start with a simple test, you should be able to take particles, pick random numbers, nothing fancy, but know what they are, set a polarizer and say, everything come out of here, I know it's that polarity. So create these orthogonal or anti-parallel particles, send them out, and if your test is unbiased, it's going to not violate Bell. If your test is biased, it's still going to violate. And somebody's got to be able to say, wow, something's going on somewhere in my experiment that's causing a false violation. So I wrote some of these rules up, and it looks, we'll do some more work with the new AI. If you haven't tried it yet, actually unbelievable. You can literally say things like, and I did this. In this last conversation with you above, you had a formula. It's got some pretty advanced physics symbols and multivariable calculus. Can you write that in Python? And it did. It was amazing. So it's like, that's the language I understand. Or JavaScript or whatever. So anyway, that was really quick. This went faster than I thought and better than I thought. Maybe I'll go through the top part real quick. This is, so my background is not like some of yours, a computer science guy. I was at ROTC, spent some time in Germany. I recently started the process of applying for a master's and focusing on AI. In the process, starting that, my daughter's at Lawrence University doing multivariable calculus, and as her teacher's saying, you should be a math professor. So I'm super proud of her, and she may be helping me with some of this stuff. And ChatGPT is my friend, just started paying for the paid version just because it's only $20, and I'll maybe go back to the free one. But anyway, study the book on relativity is an infield thing. I mentioned that Isaac Newton. I thought that was pretty cool. I love this idea because basically the idea is you prove that there is an absolute rotation in space with his experiment. Read about it. It's like there can only be one. If he spins buckets and this is like, I won't go into that, another subject, but it's pretty cool. And I've got this little site kind of like that Chantal does, some of these over the years, and this was 3 years going to this experiment and 3 years. But anyway, I some of these ideas I had, and I read stuff and it's like, oh, this is so neat. Okay, experimental slides, went over that. Yeah, this is most of it. I guess I can go to questions now. What do you guys want to see? I'm done.
Well, thank you very much. I love it because that's exactly,
Yes.
I feel like they're all one, you understand one experiment, and I actually have the data and I simulate it. Now there's a new experiment. It's like, come on, I have to read this again, ask for the data, write simulation. It's like it never ends, right? I mean, maybe like you, Richard, you understand all of them, but it's really hard to keep up with all these experiments. So I really love the idea of control experiments. Just doing a control that proves that there's no bias, because there's so many parts involved, so many steps involved. I mean, it turns out years later we find some issue with the experiment. It's like, we wasted a lot of time. So I would love that. I think that makes a lot of sense. So are any other opinions on this topic about controlled experiments?
Can I just ask a question to James? James, can you go to the beginning of your paper where you had your simulation running, please? Where you
yes.
That one there. Now, if we look at your first table there, where it says E1 A or A prime and B or B prime, and you've got 0 and 22.5 degrees, you know, that is all okay. If I read the Friedman's PhD thesis on how they did the first experiment, sorry, I see that
I added Eberhard.
I'm really ghosting them. My apologies. Let me switch this off. Basically, where do I take off this background? Anyway, let's just keep me ghosting there. Basically, your summation should be. Your summation should be over, instead of 0 degrees, it should be alpha plus 0 degrees and alpha plus 22.5 degrees. And that alpha should again be a random angle between 0 and 2 pi. Do you do that?
I'm struggling to even keep up with you. And I did this 3 years ago. I think Chantel helped me with some of this stuff. The main thing I'm just using with this is showing that it's easy to violate. I would love to make this better. I'm sure it's way out of date, but just the kind of concept, what I'm kind of focusing on more now is just the control test. Can I just, get what's a good control test setup and let people do that? And this was just a good demo, but I would like this to be accurate. I think I need to fix one of the modes for the Eberhard stuff. But yeah, basically I can explain to you in general what I remember from 3 years ago. So at this point, we can see the particles going out. It's, I have no idea what they are.
The particles are pre-polarized up or down.
No, not in this mode. Right now, we're simulating quantum. So when this leaves, and this is not a control test, this is simulating quantum. So this is very different. So what this is doing is trying to say, okay, if I'm a computer and I'm going to follow quantum mechanics, I'm going to do what quantum mechanics says, what should happen? Okay, so I start particles, and I'll freeze that again when they start coming out. So I emit particles. They have no variables. I literally have variables to say, what's my spin? They're empty right now. So what happens then is when they hit the deflector, it's going to adopt that, either that, it's going to randomly adopt either parallel or orthogonal, one of the two. And then when it does, its parent particle over here is going to be just the opposite of this particle. It has no relation to this polarizers. So really, whatever one hits first, that one becomes polarized, talks to the other one and says, oh, be opposite of me, and then it hits this polarity. And then the math just works out. So it's basically literally simulating quantum. When you do a control test, that's when you have to say, oh, well, you're going to have a really simple experiment where I do know what these polarizers are going to be. And I'm also going to have to say, if my experiment has like quarter plates and is rotating, if we go back to the to a control test is going to use classical particles. All this sounds really counterintuitive, but if you read it, it's like, so the control test, I need to fake just to show that I'm capable of, and this is a control test, it's only going to need by the ERP people. But if I'm going to fake a violation, then I've got to pre-polarize these exactly 90 degrees or parallel with one of the deflectors, one of them, and then that's opposite the other. So that's that test. But I don't think people are going to even need to do that, because most people are going to say, you know what, I just want to prove that my experiment that already violates is also capable of non-violating. In that case, you do what I'm doing here. This is actually this test. Really simple. You just emit particles, pick a random polarization, make the other one orthogonal or anti-parallel, know what it is because you set some polarizer, let it through the test. So you just keep ranging randomly, and you should not violate, like this one won't. So I think that makes it pretty applicable to a lot of tests that already violate. You run this easy test, and it's like, oh, wow, this one's violating too. Why is this violating? So if you're getting numbers, let me go back to fast mode, that are violating, I got to ask why.
Yeah, but it's violating because you already set it to those specific angles. And then Mahler's law comes in. And then, so that is basically a control test would be just two random particles with random polarization. Now, Can you do that?
Yes, yes. Well, that I'm not sure if I understood exactly what you said, but I heard the control test. So this is literally a control test. You do what I'm doing here for real. So if you have a regular, quantum test you've already built, it violates. Now you want to control test it. All you need to do is create a different emitter or put a little polarizer that constantly randomly flips between the emitter and the start of the experiment. So, and just randomly, and I'll just put this back on slow, just randomly emit them. Now, what and ChatGPT confirms to us is these should not violate. If you do that, you shouldn't get a violation. So suddenly before, when you were running it and you didn't know, when you didn't pre-polarize, they violate. Now that I pre-polarize it, very similar to what I heard first speaker Mark talk about, he put these quarter plates in and stopped violating. So that's interesting. And I need to get that in my head. But if that's actually what I'm losing my train of thought. But I'm going to stop talking because I lost my train of thought. Go ahead.
Okay. Is this available online somewhere? Then I can experiment.
Yes, it is.
Understand it.
Let me put a link there. And granted, this is 3 years old and I haven't updated it, but it just runs in a browser. You just go to the page and it just runs. Let me give you the. This is our website that someday will be hooked to ChatGPT, hopefully sooner rather than later.
I guess the point is, there are these bell deniers like I am. I'm skeptical. I'm not a denier. I'm just skeptical of these complex experiments, is there really no bias and so on. So with a control experiment, you could rule that out. So you run it, ideally even blind, in a sense that the experimenter wouldn't know in which mode it's running. Is it now using the entangled photons or not? That will be perfect. Like you do when you do a medical, tests for new medications, you do double-blind studies, right? That would be perfect. So then, and you still get the validation there only when you have entangled photons. That would be really a strong proof, in my opinion, because then you rule out all of the bias, basically.
Wrong one, delete.
So if somebody claims that he can violate Bernoulli inequality, I suggest trying with these mermins, tossing 3 coins, at least 2 are the same. How to violate it? So it's completely crazy, but you can do it. Quantum formalism allows for that. Ising model also allows for that.
So the model allows it, but the experiments are there to prove it, right? So now the original, I think we all agree that the original CHSH experiments, they were flawed, right? But people didn't know it at that time. It sounds like when I read Bertelsmann Sachs, it sounds like they thought that was at that time, they thought it was a good experiment. But later we find out, we can actually violate it because of this detection loophole. So if they had done a control experiment back then, maybe we never had this discussion, right? So, and maybe now with these modern experiments, they sound really good to me. Like I just read the one that Richard advertised, I think device-independent quantum key distribution system. That sounds really great, actually, but it takes a while for me to understand it. And who knows, maybe there's some issue in there I haven't, I don't understand yet. So I wish they would do control experiments. Then it would be much easier, I think, to believe these experiments.
Chantal, already in 1970, we knew about the detection loophole, and Pearl figured that out. Now, when Aspect did his experiment, he invoked the, the no enhancement hypothesis, which is a physical assumption that the missingness of photons is not connected to the settings. And that was the basis on which he concluded that he'd found something exciting. And this was known back then too. I mean, I think probably lots of people didn't know all these subtleties, but all these things have been known for a very long time. Nowadays we have experiments which do not have a detection loophole, I believe. And these are the Munich and the Delft kind. They are subtle and they are more complex because they are 3-party Bell experiments with 3 people with doing measurements on 2 pairs of particles. So that's 4 particles, 2 of which are interfering at Charlie's place and being measured, getting one of 4 different outcomes. And Alice and Bob all the time are busy measuring their particles at their places, not knowing what Charlie is seeing. And I'm a little bit concerned about how well those three measurement stations are all separated from one another, because in a number of the most recent publications, you see that Charlie and Bob are basically sitting in the same lab, and I'm not quite sure if that's okay. So I'm all for people being skeptical. I'm being very skeptical, but I think they should look at the more recent experiments where people have done their best to take care of everything which we knew was wrong in the past. And yeah, that's just my opinion.
So do you think it would be hard to do a control experiment? I mean, it would be possible, or what kind would you recommend if you?
Well, don't ask me. Ask the experimenters. The problem is going to be to convince them to do an experiment which they think is a waste of time.
The beauty of this thing, I think, is that it looks to me like the clear non-violation should be an easy test. But what I look at is the difference between Hubble and Webb. Webb tested the heck out of everything. No matter how sure they were, they tested it and they tested again and tested over. Hubble said, we are so good at the math, at least the management did. It's like, we know this will work. Send it up. Didn't work. They didn't account for a bolt in a test. You know, it's, I think this stuff's so complicated. As a programmer, I've learned to test everything. I just learned. There's just so much going on. It almost looks like it's non-deterministic when I know it is deterministic. So that's my take. I would love to see somebody do an experiment and try some control tests. You know, maybe Marc Fleury.
Jarek, is it possible for me to ask a question to Marc, because I think I didn't complete my question with Marc.
Yes,
and I don't know if Marc is here. If Marc is here to answer, I will get. So can I share my screen? Hey, nice to see you. Can I share my screen for a moment?
Sure.
Because I think, you know, it's better when there is a picture, because so this one here is a paper by many of you may be familiar, many not, but this is a paper published by White and others with Zeilinger, yeah? And also you have Yang Huoxi and other people there. Okay. So there, so if you need me to wait for a moment, you can read it, I will wait. But
did Verbos give that to you? That's the
no. This I found. This I found in the internet when I started my experiments with at the lab in Auckland University, and you know, and so this particular experiment is the baseline we replicated to then tweak stuff to get into the things that you know, that are questionable about I would call it correlations instead of entanglement. Okay, so I wanted to see that, and I wanted to see the, you know, the effects of the phase and that. So this is a spontaneous parametric down conversion type 2. All right. So these are the two cones, and here in the intersection of the two cones, which we photographed too, you have this state. Generally speaking, depending on how you prepare that state with this angle here, you will have a psi plus or minus. And if you put a half-wave plate in the middle, you'll have a phi and minus plus. You will shift that state to that state. And this is the diagram, which is pretty clear. And this is what we reproduced. And we reproduced these results with a little bit better precision even. So I may not have understood how you manipulated your half-wave plate or your quarter-wave plate, but in this setting particular, I guarantee you that these violations are obtained. We replicated that, and I'm actually running now one experiment remotely from 300, you know, like 300 kilometers away from the lab. So, and so this is what I mean, yeah? Now, my question mark here, it's a very important one, because these guys talk about the quarter wave plate in here. Okay, so let's see. Here. So they talk about the quarter wave plate here, and they say using an additional bifringent phase shifter, slightly rotating the down conversion, the value of alpha can be set as desired to the value 0 or pi. Somewhat surprisingly, a net shift of pi may be obtained by 90-degree rotation of the quarter wave plate. That statement set my alarm bells. So I thought, well, what is this phase shift? And then I've been talking with a physicist in Salerno, Giuseppe Vitiello, who is a really good physicist in condensed matter physics. And he has proposed in that chamber where, or table where the experiment of down conversion is performed, that you can have maybe a condensate, which could explain the correlations without this spooky at a distance interpretation. And then hearing your talk, I've read your paper some years ago because you sent them, or Paul sent them to me, but I think it was you. And I really enjoyed the fact that you were trying to explain the correlations without getting into the Copenhagen interpretation. And so for me, that was very interesting, and it still is. So I am working to show that regardless of how you conceptualize that, hidden variables or condensates or whatever, we cannot equate entanglement with correlations. And we can show that with this kind of experiments, which they didn't show here. They just tested the correlations of four Bell states, the 4 of them. So we reproduce that and we show some other things with the shift. Now, with the paper you wrote with Paul Werbels, and it's in ResearchGate, as far as I saw it last time, you played with the phase shift of a quarter wave plate, okay? And that was significant because your oscillations changed. They were attenuated when you put a very slight angle on the quarter wave plate, which is not usually used. Well, I've done a whole spectrum of that. And I think there is a lot to learn from that. And I acknowledge that. I acknowledge your work in that paper because that was kind of a pioneering work with Paul Werbels on how to play with the quarter wave plate to shift the whole, the whole understanding of what's going on in there. And on top of that, he probably brought the Markov random fields and other kind of ways of, density matrix to understand how to deal with noise. Well, we reduce the noise and we don't use actually density matrix, even though we could, but we use the quantum mechanics formalism to show that these phase shifts are not necessarily entanglement. They are correlations, yes. And you can shift the correlations and restore them after measurement. You can restore them on the go. You can do so many things in there. And that's what I'm trying to, at the moment, organize to publish, because I don't like, I just dislike that. I want to question the field. I just want to see what's really going on there. And I think that's where I'm coming from.
Shift this discussion to the end, and then we should now start with the next talk.
All right. Okay. Now you understand my point, Mark.
Yeah. I got you. Can you just 1 second go back to the top of that?
Can I just interrupt a minute? Can we have this discussion when we finish?
Yes, absolutely. Let me just take that
discussion to the.
That's good. Thank you. All set.
Yes. Post the paper, please, in the chat.
Yeah, sure.
Okay, thank you. I'm just going to finish the formal talks and then people can discuss as they like, I guess. I'm not going to show any slides, by the way, so I'm just going to talk. And just to give you some background about myself, I'm a professor of physics at Oxford. I did my PhD in general relativity and quantum gravity. I spent most of my career working on nonlinear dynamics relating to climate change. And actually, I've just written a book. It's called The Primacy of Doubt. It's about the science of uncertainty, and it's almost certainly the only book that includes chapters on quantum foundations and climate change. So if you want, let's say, an unusual perspective, do buy it. I've been writing papers on superdeterminism and nonlinear dynamics in the context of Bell's theorem since 1995. I think I possibly predate Gerard 't Hooft in this area, but it's kind of been a sideline of mine. It hasn't been my main activity, but it's something I feel as strongly about, and I feel as strongly that it's an area that's been misinterpreted over the years, and that's what I want to talk about. And in fact, I came into this seminar, this current one, rather late, and sort of the reason I did it was I was sitting, as one does perhaps these days in the evening with nothing much to do, and 20 years ago you just switch on the TV, but now you just kind of randomly go through YouTube videos. And I came across an interview of Tim Maudlin by a guy called Kurt Jaimungal, who I don't really know. But anyway, and Tim was giving an exposition about why superdeterminism was completely ridiculous. It was complete nonsense. Nobody who kind of counts themselves as a scientist should even think about it. It's not scientific. It's almost the worst possible thing. And he brought up the example, which people probably have heard before, of a drug trial. Or this was actually a case of I think the example he had was splitting a group of rats, 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 into two groups with a randomizer, some random number generator. And one group gets put into a chamber with a lot of smoke, and the other group doesn't. And you find sometime later that the group of rats that have been put into the chamber with smoke get lung cancer, and the ones that don't. So the question is, can you deduce that smoke causes lung cancer? And Tim's point was that, well, if you believed in superdeterminism, then you would believe that there could be some weird correlation between the rats, the properties, the sort of genetic properties of the rats, and the number generator, the random number generator, which somehow kind of invalidated the obvious conclusion that the smoke caused cancer. So he was kind of making the point that if you believe in superdeterminism, the whole scientific method goes out the window, and you can't do science, you can't do anything. And that kind of, that sort of thing, I've heard that argument many times. It always annoys me because I think it's a misinterpretation of superdeterminism. But what really got me going in this particular video was a particular comment that Tim made, which was that he said that anyone who believes in superdeterminism should read John Bell's paper, Free Variables and Local Causality. So it's in the famous Speakable and Unspeakable collection. It's a paper that Bell published in 1977, and it's called Free Variables and Local Causality. And Tim Maudlin was basically saying, anybody that would dare to propose superdeterminism as a solution should read that paper first, and he or she would get disabused of that idea. So this struck me as bizarre, because I have read this paper, I would say, hundreds of times over the last 30 odd years that I've been kind of proposing this notion. So what I want to do in this talk is actually go through what this damn paper says, so we're all on board with this, because I think people quote Bell sometimes and sort of, it's a bit like the Bible, they quote things that actually don't really exist in the Bible. So let's be clear about what he says. So Bell, and actually this is something where Tim Maudlin said as well, that the notion of free will here is a little bit of a red herring. And that's kind of a point that Bell also wanted to draw out in the paper. And to do that, he says, let's imagine that we set our measurement settings, our polarizers, with the output of a pseudo-random number generator. And this pseudo-random number generator the output is sensitive to the millionth digit of the input to the pseudo-random number generator. So actually, I'm going to read what Bell says. To illustrate the point, suppose that the choice between two possible outputs, this is outputs of the pseudo-random number generator, corresponding to A and A prime, depended on the oddness or evenness of the digit in the millionth decimal place of some input variable. Okay, so that's fine. Then, he says, fixing A or A prime, fixing the output, indeed fixes something about the input, whether the millionth digit is odd or even. Okay, that's fine. Now, this is the crucial sentence. This is the crucial sentence which I want to read and I want you to focus on. But this peculiar piece of information is unlikely to be the vital piece for any distinctively different purpose, i.e., it is otherwise rather useless. Okay, so he is saying, let's imagine, you are an alien living on the Andromeda galaxy somewhere. Your life is completely unaffected by whether that millionth digit is odd or even here on Earth. I mean, that's the kind of intuitive, that's the intuitive thing that probably most people would imagine is kind of a reasonable assumption. Okay, so I'm going to take that just a tiny bit further and just express that a little bit more mathematically. So let's imagine, indeed, let's think about the whole universe, or if you like, our local cluster of galaxies, doesn't really matter. And we're going to imagine a state space which encompasses all the degrees of freedom of all the stars and all the atoms in the stars and everything else. We've got some humongously big state space. And the state of the universe at some time, I just represent as a point in this humongously big state space. And I'm just going to label that point, let's say, with a capital U. And included in that state is this notion that we have a random number generator here on Earth, which has been fed with an input variable, which has as its millionth digit a certain number, which is either odd or even. Let's suppose it's odd for the sake of argument. All right, now what I want to do is consider this question that Bell assumes is correct about whether that millionth digit is relevant for any distinctively different purpose other than for setting the polarizer for a Bell experiment. All right, so I'm going to imagine mathematically creating a hypothetical state of the universe, which is absolutely identical in every respect, except that the millionth digit, the millionth input, except that the input variable differs from the actual one by the millionth, at least the millionth and perhaps beyond the millionth digit. So it's a very, very slightly different input number, which has a different millionth digit. So what I'm doing is I'm taking that point in state space and moving it very, very, very slightly in the direction of the variable that corresponds to this input variable to the pseudo-random number generator. And I'm going to call that U prime. Now, it's a hypothetical state of the universe, doesn't really exist. So what's my intuition about U prime? Is it a sensible state of the universe? Well, Bell's intuition is it should be a sensible state of the universe because, the rest of the universe can continue on exactly as it does, whether or not the millionth variable is odd or even. But I want to ask a rather deep question. Is it inevitable that that slightly perturbed state of the universe is consistent with the laws of physics, whatever the laws of physics are? Is it necessarily consistent with the laws of physics? Now, I want to make the point that actually I think Bell himself realized that that was a key question in his theorem. And to make that point, I'm going to turn back a page in Bell's paper and just read the following paragraph, actually. So just when I read this paragraph, just think about this U and U prime. U is the real world. U prime is a hypothetical world, which is where the moons of Jupiter are exactly as they were in the real world. Everything is the same, except that the millionth input digit is different. Okay, so here's what Bell says. I would insist here on the distinction between analyzing various physical theories on the one hand and philosophizing about the unique real world on the other hand. In this matter of causality, it is a great inconvenience that the real world is given to us once only. We cannot know what would have happened if something had been different. We cannot repeat an experiment changing just one variable. The hands of the clock will have moved, and the moons of Jupiter. Physical theories are more amenable in this respect. We can calculate the consequences of changing free elements in a theory, be it the only initial conditions, and so can explore the causal structure of the theory. I insist that what he calls B, which is his paper Theory of Local Beables, I insist that B is primarily an analysis of certain kinds of physical theory. Okay, so with that point in mind, I want to ask the question, could one envisage a type of physical theory where a hypothetical perturbation to just one variable of the state of the universe is actually inconsistent with that theory? Can one imagine that such a theory, could such a theory exist? What would such a theory have to be like that? Now, I would say in ordinary classical theory, you know, we have initial conditions, we have laws. Sort of, we decouple the two. Classical theory, the initial conditions and the laws are totally decoupled. So we can perturb the initial conditions, any initial conditions, as we like, and then we just run our evolution equations from the perturbed initial conditions. But there is a type of theory where that's not true, and I was kind of curious to note that Álvaro's talk, I guess on the opening slide, had a picture of a chaotic attractor. And there is a class of nonlinear theory, and this is the class of theory that interests me. A class of theory which is deterministic, but it's nonlinear, and it has the property that if you define the dynamical system by differential equations, and you let the system run from a sort of an arbitrary initial state indefinitely, it will eventually or asymptotically evolve on a special measure zero, what a dynamical system person would call an attractor. I would call it an invariant set. It's the set of points in state space under which the state is invariant under the dynamical evolution law. Now, I mean, the very simplest types of invariant sets are just what are called limit cycle. Well, actually, a very simple set is where you have a state which goes to a steady state. So you have a fixed point. That's the simplest type of invariant set, a fixed point. But that doesn't describe the world very well, because that would be completely static. Then you have limit cycles where the system is periodic and it just goes around a particular orbit forever and ever, just repeating itself. But the much more interesting class of invariant sets are the chaotic ones, which are fractal, and in some sense those are the most generic. But all of these invariant sets have the property that they have a measure of zero relative to the Euclidean n-dimensional state space in which they're embedded. And what that means is that indeed, if you take a point on the invariant set, on the attractor, if you like, and randomly perturb it, let's say in one direction, when I say random with respect to the continuum measure of the Euclidean space in which this attractor is embedded, then with probability 1, you take that point off the invariant set into its neighborhood, maybe into a kind of gap in between the trajectories. So we have a potential class of theory where actually Bell's example, or Bell's intuition, if you like, that the value of that millionth digit was irrelevant for any other distinctive purpose other than for setting the polarizer, is false, in the sense that randomly perturbing that millionth digit, keeping everything else the same, takes you off the attractor. If your theory demands that states of the world evolve on this invariant set, then what you've done is violate your hypothetical, what a philosopher might call counterfactual perturbation, has now violated your laws of physics. Now, I'm not, in this talk, I don't want to convince you that this particular dynamical model is correct. The only point I'm making is that it's a theory, and that's what Bell was saying. He said, don't philosophize about this because that's going to get us nowhere. If you think my intuition is wrong, come up with a theory where it's wrong. And this is a class of model where that intuition is wrong. It's not, just to be clear about this, it's not that the alien on Andromeda suddenly, whoa, what happened? Somebody changed the millionth digit of a variable back on Earth. It's just that the laws of physics are inconsistent. So that world U prime will never be realized according to this particular theory of physics. So in that sense, it's a sort of an existential perturbation on Earth, for the moons of Jupiter, for Andromeda, for everywhere. It's just like the whole universe goes up in smoke if you were to perturb that millionth digit, keeping everything else fixed. So in my view, this is actually fundamentally what superdeterminism is about. I mean, the technical definition is, and actually this links a little bit to Robert's talk, it's about whether your probability measures a superdeterministic theory is one where the probability measure on the hidden variables cannot be treated as independent of the measurement settings. But the way in which that is violated is by doing a counterfactual perturbation on either Bob or Alice's setting and showing that keeping the lambda fixed, that hypothetical universe would take you off this special set of points, this invariant set, and so would be inconsistent with the laws of physics. Now, it's worth saying at the end here, well, I want to make 2 points, see 20 past. I want to make a couple of points and then I'll finish. Magdalen's categorical that this is a rubbish idea. This is not even science. It should be pointed out that Bell was much, much more ambivalent about this. And he says at the end of that paper, so this is my third and final quote from Bell, of course, by the way, of course, he starts the paragraph with the 2 words, of course, it might be that these reasonable ideas about physical randomizers are just wrong for the purpose at hand. A theory may appear in which such conspiracies inevitably occur, and these conspiracies may then seem more digestible than the non-localities of other theories. When that theory is announced, I will not refuse to listen either on methodological or other grounds. So it's a great tragedy that we can't discuss these things with Bell. I would like to have thought he would be, well, let's say at least interested in these proposals, and certainly not as dismissive. And Magdalen's not the only one, I should say. I mean, there are a number of other people who make similar points, and are very so completely dismissive. I just think it just shows people are not thinking, out of the box, if you like, about the type of physical theory we may need to explain Bell's theorem. Now, one reaction I get when I try and publish papers, I get reviews saying, God, is this what we need to solve Bell's theorem? I mean, is non-locality that much of a problem? I mean, my view is, as I say, my PhD was in general relativity. General relativity is a deterministic, locally causal, nonlinear, geometric theory. Quantum mechanics is linear, if you believe in Copenhagen, not deterministic, seems to violate local causality, not terribly geometric. So I take the view that the difficulty we have had synthesizing quantum mechanics and general relativity just comes from that fundamental incompatibility, and that finding something that can explain quantum physics but is non-linear, locally causal, geometric and non-linear, I think is a great goal to aim for, because that will hopefully make this synthesis much easier. So I'm just going to end with the drug trial. I think the point I would make about the drug trial is that, see, the key point I'm trying to argue here is about whether counterfactual worlds are necessarily consistent with the laws of physics. Of course, it depends what the laws of physics are, but I'm suggesting at least a class of so just to be clear, my idea would be that the universe as a whole is a deterministic dynamical system evolving on some super cosmological attractor, fractal attractor, and it goes through maybe multiple epochs going around and around this attractor, but basically that's what it is. And counterfactual perturbations to states, in other words, ones that you make from just hypothetical assumptions without any particular constraint with the dynamics, they are typically going to take you off the attractor. By the way, the philosopher Michael Redhead wrote very persuasively years ago about the importance of this assumption of counterfactual definiteness in the Bell theorem, and this is really what I'm kind of saying. There are classes of theory which seem to me perfectly sensible deterministic theories where counterfactual definiteness is violated. So I'm not saying all counterfactuals are wrong, but there's a class of counterfactuals that would be inconsistent with the laws of physics. Now, just to say, what's this got to do with drug trials? I don't think it's got anything to do with drug trials, for the very simple reason that experimentalists don't ever make use of counterfactual reasoning to justify their experiments. If somebody has done a drug trial on a group of rats and says, I'm a little bit worried that there may have been some spurious correlation between your randomizer and the rats, God knows what that is, but then the experimentalist will say, okay, well, we'll repeat the experiment with a different randomizer, or we'll let another group in a different part of the world with a completely different setup do the experiment. And that's the crucial aspect of what that makes experimental science scientific. It's the ability to reproduce experiments. It's reproducibility. I mean, that's why cold fusion, got nowhere, because nobody could ever repeat those cold fusion experiments. And that's the key. It's not, believing in counterfactuals is not something an experimentalist, unless they're, at night they're a kind of a part-time metaphysician or something where they might worry. But the scientific method doesn't pay any attention to counterfactuals. So that is just an illustration that this kind of drug trial thing is just a grotesque in my view, sort of caricature of what is actually a much, much more subtle assumption in Bell's theorem, which may be false. I mean, I don't know, who knows, but I'm just saying, I think one can envisage a class of theory which violates this counterfactual assumption. It allows experimental science to carry on without any impediment at all. And but on the other hand, I do think, I would argue, see, who invented or who discovered, say, fractal attractors? It was a colleague of mine, Ed Lorenz, from MIT, a meteorologist. So in some sense, I tend to think of fractal attractors as kind of post-classical. They're not really classical. It's an interesting question whether you call them classical. I tend not to call them classical. If you read my book, there are many beautiful. You can do things like discuss Gödel's theorem in terms of the geometry of fractal attractors. You can talk about p-adic numbers. I mean, beautiful ideas in number theory come out of looking at these things. So my view is that they are kind of post-classical. So I'm not proposing a classical solution to Bell's theorem, just to be clear. I'm not doing that. I don't think there is a classical solution unless you're prepared to, swallow non-locality, which I don't find a very appealing idea. So this is non-classical, but it does preserve locality and determinism, and it attacks what would be called the statistical. It's kind of a bad word, by the way. I don't like it either. Statistical independence. That thing with the probability density is sometimes called the statistical independence. Again, you see, it conjures up ideas in people's minds, and I don't think that's a good thing. But anyway, that's it. I think that's pretty much, done. Thank you.
Thank you very much. So now we'll discuss any questions, comments. So let me maybe make one comment. So you could talk about the general relativity. So this is for me a very nice example that we shouldn't use Euler-Lagrange equation. That Euler-Lagrange would mean that the space-time unrolls, which kind of makes little sense. How we solve general relativity is the least action principle, saying that we have some 4-dimensional Gelo which minimizes tension. So why shouldn't we just try to solve with the least action principle? It is also super deterministic, and I can argue that it violates Bell inequalities.
Again, I don't want to get into the argument my idea is better than yours or anything like that. So all I'm saying is, if you go into Euler-Lagrange, you've got these issues to do with the past and the future boundary conditions. And the great thing about these fractal attractors is there are no boundary conditions. There's no initial condition. There's no final condition. These things they go on forever in the future. They go on forever in the past. So it's a way of completely, the whole kind of retrocausality stuff. It doesn't play a role. The boundary, there's no role for boundary conditions. Now, on the other hand, I don't know of a simple, if you like, Euler-Lagrange, and this is something I do think about, but I haven't come to any profound conclusion. I have yet to kind of come up with any kind of simple, let's say, minimization principle like Euler-Lagrange, which could generate one of these fractal invariant sets. We know they exist. I don't know how to formulate them in terms of a minimization principle. It wouldn't be something simple like Euler-Lagrange. It would have to be more complex and almost certainly based on p-adic numbers, which are the sort of natural mathematical tools for describing analysis on fractal geometries. Your idea kind of invokes the future and past boundary conditions in some kind of symmetric way. My approach, the time boundary conditions don't play any role whatsoever. That's all I got to say, really.
So this fractal is inside the space-time as a subspace of subset of space-time, yes?
No, it's not space time. No. This is important. It's a subspace of state space. This is like a super important point. It's not space time, and
it's a
space. Kind of a curious question to know. Sorry, I missed. It's state space, yeah, fundamentally, and that's super important because there are no. State space doesn't come with a causal structure. State space doesn't come with a Lorentz, metric or anything like that. The space time does. So these holistic structures, they don't violate any causal, properties because they aren't. They're constraints in state space, which doesn't have a Lorentzian metric.
So I have a question.
Yeah.
This, this fractal set concerns hidden variables related to the particles, the fields, or both, or what's your
both.
idea?
I would say both. I definitely agree. I think it was your point, was it, Álvaro? I can't remember now. That one shouldn't think of the hidden variables as localized to the particles. In some sense, the support of the local variables has to be quite broad. But, as I think Richard said, Bell's theorem doesn't say anything about, local variables being localized onto particles. So, I think he was probably right. Just to say you've got somehow a delocalized hidden variable quantity doesn't itself explain, can't be used to explain the violation of Bell's inequalities in a deterministic, locally causal way. So there's more to it than just saying the hidden variables are somehow delocalized. But I think it is a consequence of my. I'd have to talk more about it, but that somehow they're not certainly they're not localized to the particle.
Okay, thanks.
I have a question. Well, Tim, first of all, it's a pleasure to listen to you. I think we last met about 10 years ago with Roger Penrose and Basil Hiley and yourself.
Oh, right.
Yeah, and we talked about some of the things that are relevant to this at that stage. We were talking about quantum events, about events that went from A to B, and retrocausality. I'm sorry I missed that talk. I was unfortunately not able to listen to that part of it. I think is part of another kind of system that also illustrates the thing that you've been looking at in terms of a bounded state in state space, a strange attractor. That is, as soon as you have something which is transactional, both forward and backwards in time, that one also has a system where one can't change the states a little bit and have something which obeys the laws of physics in for the whole of space and the whole of time. So I think that's another example of a system which fixes the whole system. One can't get a finger in between what Alice and Bob are looking at and what's happening in the detectors, because the whole system is both forwards and backwards in time.
The thing though is, I think my so I deliberately tried to avoid talking about anything technical, if you like. But I have I do have a kind of a technical. I could give another hour's talk on the sort of technical side of it, and one way of actually talking about it is in terms. I'll come to your point in a minute. Is about the thing about Max Planck introduced his quantum hypothesis as a way of sort of discretizing the energy of harmonic oscillators and things. But we've ended up with a theory where the continuum still plays an absolutely 1,000,000% critical role, which is the continuum of Hilbert space. Hilbert space, is a continuum space. And indeed it's a vector space over complex numbers, the continuum of complex numbers. Now, one way of formulating my approach is actually quite simple, and that is to sort of discretize Hilbert space so that the coefficients, if you like, in front of a sort of set of basis vectors for a quantum state are the amplitudes are rational numbers, and the complex phases are rational angles. Now, what this gives you is something kind of subtle. When you apply it to the, let's say the CHSH Bell theorem, so you have these 4 different possible pairs of angles for Alice and Bob, 0, 0, 0, 1, 1, 0, 1, 1. And you say, well, let's consider a particle where Alice and Bob measure, let's say 0, 0, for the sake of argument, could be choose whatever you like. Then the other 3 options, let's say 0, 1, 1, 0, and 1, 1, are all counterfactual for that particular lambda. Now, in my theory, it's not the case, actually, that all 3 of them are disallowed. It's actually only one of them. I mean, we don't know which one, but 2 out of the 3 counterfactuals are allowed by the theory, but you can't, all 3 counterfactuals are not allowed. So you violate. So what I'm saying is, I've got a little bit more flexibility than perhaps you're suggesting. I'm not saying that absolutely everything is fixed.
I wasn't saying you're right.
There are many counterfactuals that are possible, that are consistent with the laws of physics. But for example, with the CHSH, the 3 additional counterfactuals for a given lambda, not all 3 of them, according to this theory, would be consistent with the laws of physics, only 2 of them.
I think that's a very interesting point, but we could get, I suppose we're now in the position where we've actually finished all the talk, so we can get properly technical. I think Hilbert space is a bit too simple here as well, because what you're doing with it, if you have a Hilbert space, you've done something before you have the Hilbert space. What you've done, there's something hidden there outside setting up a Hilbert space, because to set up a Hilbert space, you have to have a system which is quantized, which is a quantum system which contains that space. You have to have a state space in which it exists.
Well, wait a minute. Stop a second. I mean, you can talk about Hilbert space for classical systems. If you want to, if you have a system that's uncertain, you could, a dice or a pack of cards. You don't know what the top card is. You can represent that card by, a Hilbert's.
That's right. But a Hilbert space can do simpler things. That's true. But taking it to the level of its ultimate complexity. So if we're looking at something which is as far as it'll go, because it's a complex number system.
Yeah, it's complex numbers that make
because it's a complex number system that you're using there. You're limited by something which is still one of the division algebras. So complex numbers being one of the division algebras, you have a state space which is defined by which is defined by your system. So you have a system. But if we come back to what that quantum system is, and this also addresses the thing with the Delft experiments as well. Clearly, in the case of photon experiments, if you have something which has an emission and an absorption, just relativistically, the emission and absorption have to take place at the same point in space-time. That means that the actual setting, whatever any Alice or Bob have done to their polarizers, is known by the entire light speed system before there is no time to do anything other than have the state as is, the physical state as exists, the factual state, not any counterfactual state. So for photon systems, you're always dealing with a single point in space-time for the emitted and absorbed photon. So all of those experiments, really, you can propose the experiment happens, but in setting up the experiment and saying that Alice chooses to do this, well, she can't, because the whole thing has happened bang at one point in space-time. So you have something which the whole premise of the idea of what you're doing in trying to set up these experiments is already flawed at the level of special relativity. Now, when you go to doing the experiments with electrons, and you start looking at electron states, in order to do things there where you're looking at entangled states or mixed states, and this may be causal as well, and I love the stuff that's been done on that. But when you're looking at those states, what you have to do first is set up a quantum state. And to set up a quantum state, you have to wait for an amount of time. You have to have it go backwards and forwards. It has to go ding, dong, ding, dong. It has to be resonant and harmonic. Once it becomes resonant and harmonic, okay, you can then let the thing out. And okay, they can sit there doing the resonant harmonic things as long as they like. Now, provided that experiment is then done within the elastic mean free path, so the states have not been interfered with, they are still ringing with the quantum state that they both had at the point they were fixed in a quantum state, which is it can be described by a point in Hilbert space, but it's more complicated than that. Hilbert space is not sufficient to describe the entire system that's sitting there oscillating, because it's not simply two-dimensional like a two-dimensional plane in quantum space. It's at least four-dimensional in space-time, especially when you're letting a thing wander around in space-time and doing things through angles. You should be thinking about things like Berry phases, for example.
Yeah.
Take something, and even doing the computer thing, which was done just now, if you run something through 90 degrees, you will get a 90-degree phase change, a Berry phase change. And that thing is not even considered in these experiments. I think it's interesting also that the thing that you highlighted, that was highlighted, that you're getting a 90-degree, you're getting a 180-degree phase shift with a 90-degree turn of a quarter wave plate. I think that's also interesting, because you're looking both forward and backwards. If you're looking at the thing as a transaction in terms of an interaction, then it's going through that thing twice.
Okay,
can I interrupt here? John, in whatever you said now, I think I might have counted 10 hypotheses in there. It was no physical reality. I think in order to really get down to the cause of the Bell inequality, we should not argue about probabilities and so on. We should really be
no, I agree.
The ontology of physics. And
I'm not arguing about probabilities, Anton. I'm talking about the actual physical space as it exists in a proper quantum space.
How do you know it? You don't know it.
Exactly. You don't know it. Exactly. You don't know it.
You know, that's the point. You know, and if I may share my screen, I've got, you know, there's a very simple experiment that will.
Could I stop a second?
Yes, of course.
We're just going off topic a little bit. Could I invite? I'm trying to read it, and I haven't really read it, but I've just read the last sentence of Richard's comment, which is something about science fantasy. And I could see he's referring to my talk. So could I just invite Richard to say whatever it is that he thinks is fantasy? I'm trying to read it.
Yes. Okay. Well, I mean, this just sounds like fantasy to me. If you can figure out a theory on this basis, which enables you to make a grand unified theory of physics and solve all the problems of the Big Bang and so on, I will be very, very impressed. But I don't think it's going to help people understand Bell experiments.
I mean, for me, it's very intuitive, but maybe that's because
for you, it's very intuitive.
I spent 40 years of my life working on chaos theory and stuff.
Yeah,
so
no, I spent my life working on chance and statistics, and I would love it that the universe is driven by quantum randomness. I have no problem with that.
Yes.
And that randomness express itself in some beautiful sort of non-locality, which allows collaboration at distance, though not action at a distance. I think that's wonderful.
Well, it doesn't make much sense to me. I mean, Einstein's famous example just of a single particle coming out from a single point source and moving onto a hemisphere of photofluorescent material.
Yeah.
The problem is, you know, he pointed out that the problem with that is that when the let's say the photon when the wave function of the photon collapses at a point on that hemisphere. If you say it's random, then somehow every other point has got to know not to collapse to produce a photon.
Yes,
so it's a weird kind of randomness. And I think it would be better to just accept there is something deterministic going on there.
May I interject?
I think one could perhaps decide to accept that there is something non-local and random in the universe.
Okay, look, Richard, I accept that, you know, people have different views, and I respect your view, but I don't think it's fantasy. I think I'm proposing something which is mathematically. So finish my sentence, just one second.
Go ahead,
I think what I'm proposing is mathematically correct and sound. Whether it's physically correct, I mean, I don't know. Obviously, you know, the $1 million, billion-dollar, trillion-dollar question will be finding an experiment which can test this.
Yeah.
My own belief is it will ultimately come when we get close to being able to test particles which get close to the Planck mass. In other words, testing quantum mechanics in a regime where the particle's gravity is non-trivial. I think that will sort a lot of problems out. We're a long way from doing that, sadly. So I think we just have to accept we have different views. But I don't think it's fantasy, Richard, with respect. I think it's sound mathematics, nonlinear mathematics, and I don't see anything particularly wrong with it. But whether you agree, of course, it's entirely up to you.
You'll have a hard time convincing me, but I mean, you try to convince some other people.
Yeah.
Tim, can I ask? I don't want to interrupt. It just John Bell wrote about the deterministic, superdeterministic, and deterministic chaos a bit you raised. It's actually just to read scripture, La Nouvelle Cuisine, page 244.
It just shows how long I've been working on this. This is an earlier edition, which came out before La Nouvelle Cuisine.
Okay, La Nouvelle. Oh, you don't have La Nouvelle Cuisine. Well,
no, it's not in this edition.
You will love this. You will love this. And by the way, just for the little story, I was with Tim Mudlin 2 months ago at his place in New York, staying with him, and that's what we discussed. And we prayed on this passage. Give me a second. Yep. An essential element in the reasoning here is that A and B are free variables. One can envisage then theories in which there just are no free variables for the polarizer angles to be coupled to. In such superdeterministic theories, the apparent free will of the experimenter and any other apparent randomness would be illusory. Perhaps such a theory could be both locally causal and in agreement with quantum mechanical predictions. However, I do not expect to see a serious theory of this kind. I would expect a serious theory to permit deterministic chaos or pseudo-randomness for complicated subsystem, e.g. computers, which would provide variables sufficiently free for the purpose at hand, but I do not have a theorem about that. Okay, so John Bell clearly, thought about what you just said, and he comes out with, look, that map between deterministic equations of GR and non-deterministic formalism of QM. Many people start with the non-deterministic of QM as the basic ontological brick, but in fact, he constructs a map via deterministic chaos. We have seen it in the walkers of Couder. Yves Couder put a walker rotating in a bath. John Bush here put it in a coral. And really what we see in this dynamic is that, the walker is basically coupled to this nonlinear surface. And so the path of the walker is a deterministic chaos. I have written a paper, it's published in Chaos Magazine, characterizing actually the chaotic phase state space of the walkers with Burak Budanur here at Georgia Tech with Predrag Zvitanovic's team here. And the Couder had already said, look, it's very possible that what we call superposition is in fact intermittence, chaotic intermittence. The particle orbits this, then orbits that. It jumps between orbits randomly. And the component that is missing, to your point, you say the fractal attractor, yeah, but that's the component that is missing, and Couder himself in the walkers insisted on this point, it's the standing little wave that's there, that information, that memory, that nonlinear memory that guides the particle and creates this path divergence. So it's the memory, according to Couder, in the standing wave. It's almost tautological at this point. A standing wave is a memory by definition of standing there. But it's a very, very fine thing. And well, being long-winded, just to finish on I did read the papers that Joshua was talking about, where they do modify the source by putting a half-wave plate in the arm, and I did not realize that. And so where I'm going with all this is, maybe the source of that little wave you talk about, the source of that non-determinism that is so critical in quantum is in fact the electron Zitterbewegung. De Broglie hypothesized this standing wave. It's enough to create this non-deterministic behavior you need, as an emergent phenomenon. That's it.
I mean, all I'm saying, yeah, I mean, it's good to hear the Bell quote. I mean, I think the problem with these little bouncing drops and so on is explaining, you know, entangled particle systems rather than just single particle systems. They obviously do a good job in explaining the you know, the two-slit experiment and things like that.
But John and Álvaro have an excellent paper on entanglement that's coming out.
Right.
It's a static test, but it's
yes. My point is that it's for the entangled, is for the Bell theorem, that this, if you like, the fact that the invariant set puts a non-trivial measure on state space, it creates, if you like, no-go regions where the measure is zero. That is the crucial thing which in my model allows you to evade, which allows you to violate Bell inequalities without having to assume non-locality. So I do think, I think, you know, it's more than just saying you have, let's say, differential equations which are chaotic, which you can start from any old initial condition. I think, you know, the combination of, well, it's basically the invariant measure, which see, the point about the invariant measure is it constrains not only the evolution equations, but it constrains what those initial conditions can be, because you can't have an initial condition on a part of the state space where the measure is zero. And that's what I'm claiming is the thing which allows you to evade non-locality. I'm pretty damn sure this is correct, but whether people accept it or find it too complicated, I can't. It's not science fantasy anyway. I think it's fairly rigorous mathematics.
Could I ask one thing, Tim, about that? And it may help me understand your point of view a little bit more. I'm wondering if it's possible to translate what you're saying into a simpler context, right? Because you're talking about a zero measure subset on a phase space, and you can't just arbitrarily perturb something from there because you will then wind up in a different point of phase space and violate the laws of evolution, right? But can you not basically make the exact same point about the wave equation? You know, imagine that you have some initial conditions, whatever they are, and then a wave is propagating through space according to the wave equation. It is then not the case that you can arbitrarily perturb from one moment to the next, say the position or the velocity of a given particle, and then stay within the confines of the wave equation. And it seems to me like that is kind of like the same point you're making, only it is maybe a little bit more simple than the way that you made it, or at least it seems more simple to me. And I guess I'm wondering if that seems on target to you.
Well, it's just that, you know, I mean, it sounds like what you're talking about is de Broglie-Bohm type theory. And
I'm talking about the wave equation, like not just the wave equation. Because I think the issue here is
about wave equation.
Yeah, so the issue here is about theories, and you're talking about like physical theories and what they do and what we can expect from them, right? And so I'm just wondering if we can't translate this exact same point you're making into the classical wave equation and look at the evolution, and you can say the same thing in there. I think
you cannot. I'm sorry, but to have a fractal attractor, you need nonlinearity, and the wave equation is purely linear. So
all these invariant sets. The one thing they have in common. One thing they have in common is that they're nonlinear systems. That's quite a fundamental point.
And you also need to be dissipative, also, because if you have a conservative dynamical system, you would have, so you are leaving something, and this has to do with radiation. Perhaps it could be, I don't know, but
can I make the point that you're right, absolutely right, to bring out there is an element of irreversibility here, but that irreversibility can be localized to an arbitrarily small region of state space. It doesn't have to be, in other words, I mean, if now Richard will just roll his eyes now, but if one is thinking about this as describing a multi-epoch universe, I mean, it could be that all the irreversibility occurs just in the transition from one epoch to the next. That would be enough to generate an attractor. You could have a dynamical system that is Hamiltonian on 99.999% of phase space, but it's dissipative on the remaining 0.001%, and that would have a fractal attractor as its invariant set. So the dissipation can be very, very localized to different parts of space and time.
If you look physically, then the phase isn't interfered with an elastic transition. If you're looking at the solutions of the Schrodinger equation, but then looking at them experimentally. So if you experimentally form an electron beam, say in the solid state, and have a look at how long the phase coherence persists, you find that the phase coherence length is longer than the scattering length, but is close to the inelastic scattering length of the system. So once it undergoes an inelastic event, then that phase is randomized. But before that, even with small scatterings that it has from one point to another, it retains phase coherence more, or appears to maintain phase coherence, in that one still gets quantum interference effects. I did an experiment on this back in 1990. There's an experiment in PhysRev on that. Just for information.
Thank you. I'm sorry to say I'm going to have to leave the call in about 3 minutes, but I'll let the rest of you argue it out. I'm just very happy I've been able to at least put my point of view over. I'm not asking any of you to believe it, but I just would say when people like Tim Maudlin sort of just completely rubbish this idea with these drug examples, I just, you know, they're not good examples to use. That's all I'm saying.
And thank you. It was a pleasure to listen to you again. So you take care of yourself, and we'll talk some other time.
Okay. All right.
All right. I just have a comment about this idea of a state space, that the state space is not the same as the measurement space. And in particular, you can have a single state and two different measurements, and those two different measurements are drawn essentially from different probability distributions.
You're absolutely right. In fact, the state space is always different to the measurement space, because the measurement is always a perturbation of that state, if there's any interaction with it. So in fact, they are separate. Absolutely correct. Yes. In fact, I think that there is a problem here, in that one often confuses the fact that the thing has to be in some specific state with what happens with the measurement, because the measurement is going to perturb that state, both in all theories, both forward in time, but in theories which deal with interactions between emitter and absorber, also backwards in time. So the measurement then is quite crucial. Where you set your boundary conditions outside of the experiment is actually also completely crucial. And each individual experiment can be done, as Tim was saying, only once. You can't. Reproducibility is so important in physics, but in this particular case, of course, you don't know where you are in the Zitterbewegung phase if you believe Hess needs a Zitterbewegung interpretation of quantum mechanics, or if you want to go for the Copenhagen thing, one cannot know where one is in the phase of the wave function. Both things give the same result. That there are certain things that you can't know about a particular state because they can't be measured by any means. And those things, that measurement is often neglected in discussions of this kind, but it does perturb the state space of the system. It puts it into a new set of, it introduces an extra dimension to the state space in which this unperturbed system sits. So it changes the system simply every time.
But even given the fact that the measurement perturbs the state, presumably the result still depends on what the initial state was.
No, a proper measurement where you absorb a quantum destroys the state. We're talking about creation and destruction operators here.
Right, but in a realistic model, that still depends on what the initial state was. So my point is that if you have two measurements that are made on the same state, the probability densities of those two measurements are not necessarily equal.
either the intermediate measurement was not carried out, or one cannot do that because the initial measurement perturbs the state for the second measurement. If you get any information out at all, that gives you information about the system, which then changes that state.
Well, I'm not using any of these non-local loopholes. Just even if it's the same state, they're essentially, those two measurements are drawn from two different probability densities.
No, I mean yes, and the simple experiment of taking two linear polarizers which are at right angles to one another, then introducing a third one at 45 degrees, that allows no light through. Then introducing a third one at 45 degrees, light starts coming through. You've changed the state by introducing an extra polarizer. You do that with any kind of polarizer, a circular polarizer an at an angle polarizer, whatever you do. If you do a pair of measurements, you change the state in the intermediate measurement. Otherwise, you haven't measured anything. You've taken nothing out of the system or into the system.
Yeah, the problem is we don't really know what that measurement is doing.
That's just what I just said. You know that it's changed it, but well, you do know how it's changed it because you've got a new set. If you take a polarizer in this direction, then take one at 45 degrees, then everything coming out will be polarized according to the 45-degree thing, and nothing at all to do with the first polarizer. Although you only have a quarter of the light, but there you go.
But excuse me, but we have to take trying to explain all of this. We must not take a sort of a local view of and say this. The state space has changed. If one takes God's view and looks at all of the universe, then nothing can wobble the universe or jiggle it.
That means that light is the God, because it can't be jiggled.
No, it's not what I'm saying. I'm just saying that that there is a universal state which cannot change. But within the universe, things can change to the detriment of something else changing, and the Bell experiments show us this. That's why we have the entanglement, because
the universe is changing all the time. Look around you; it keeps changing.
Yes, it's that what we see. That's what we see. But from a conservation point of view, or from a Noether's point of view, if we take the whole universe as an entity, nothing can change it. That is, if something changes here, something else has to change somewhere else, that the whole thing stays in balance.
Are you suggesting that Alice and Bob sit there frozen in space and time as a single point in the whole reality of all space and all time? Because
no, I'm not suggesting that. What I'm suggesting is that the whole ontology that we use to describe physics is wrong. I'm developing a new ontology, which I will be presenting in 2 weeks' time. And, and therefore my view is completely different. And if I just may share one slide that, which is for today's talk. Now, hopefully, there you can see it now. I devised a new Bell experiment without correlations. Alice on the right-hand side has a 25%, 75%, or a 75-25% polarizer. And Bob on the other side just uses a 50-50. And I predict that Bob will see a skewed polarization. Now, if that experiment is performed and that comes out, we really have to rethink what we have to do. And poor Richard will be out of a job in this group.
I have performed something similar. This was one of my starting points, putting circular polarizers and testing that, because if you put, if you filter out one circular polarization, you have it in the other, it's not. It comes with a null result. I mean, I'm happy talking more about that, but I don't want to. There's nothing there. Well, I thought it was a good idea.
I doubt it, because that paper that Joshua showed us, where they introduced these half-wave plates in the one leg.
Yeah, that's very interesting. I just read it.
My point.
Yeah, that's fascinating.
That proves my point.
No, time out. Again, that was my starting point. Let's polarize circularly. Let's select one, because it's going to be untested. The whole idea that, if you put two perpendicular and you do circular in between, you're going to get a signal. So let's do it on one arm. Let's do it on the other. I did that experiment with the quarter waves. Nothing comes up. It's an illusion. It's a narrative. I had not seen the stuff Joshua sent, and just for reference, that's what he sent before. Now that is fascinating, because essentially what Zeilinger and Xi saw in 95, published in PRL, is that sentence he showed, which is somewhat surprisingly, a net phase shift of pi may be obtained by a 90-degree rotation of a quarter wave plate in one of the paths. Now that's fascinating, because I counted him before, because I never encountered this idea, but okay, if we put a quarter wave and we change between psi plus, psi minus, that's how we prepare the states in the actual pumps. But here what they do is they put the quarter wave plate downstream, not in the source, but downstream in the measuring apparatus. And I was telling him, dude, that doesn't change anything. That's not how we change the psi minus. Actually, they saw a change. And so this goes to what I was talking about earlier. We discard the idea that the polarizer have a fundamental immediate influence on the source. And that's what these guys saw. If they put just one quarter wave plate down, it completely changes the phase at the source, meaning the crystal actually contorts itself to emit the two cones so as to match what's going on. And Paul actually insists on, look, we may need to revisit Klitschko and what's going on in the polarizers. We have no idea how the actual absorption is being made and re-emission. We may be missing a big thing in how the polarizer is coupled to the source. So, just to wrap it up, I've tested those ideas with the circular. There's nothing there. The Xi stuff I'd not seen, and that is really interesting, actually.
You have a reference for that? Did you get it published?
The work, Paul and I have written the work. We've tried to publish. Paul wraps it up in a narrative of retrocausality, which gets shut down, but we have the data published, and we can send that to you. I'm not going to say it's
I'd love to see it.
It's not
yes,
up for publication, but we do have 2 papers on the quarter wave plate stuff. I'm happy to share that. It's not
Thank you.
public. Yeah.
Thank you.
But the Xi stuff and Zeilinger is PRL 95. And that I had not seen.
Can I ask you a question, Richard? So I very much appreciate you being here as a representative of the fundamental randomness of reality school.
Yeah.
And I have a general question about your intuitions along those lines, because if we have entangled particles and we measure their spins and the magnets are perfectly aligned, say, we will always get, say, Alice sees +1 and Bob sees -1, right? And then Bell said that this fact seems to cry out for the existence of a hidden variable explanation, right? Because you have basically perfect correlations or anti-correlations in certain physical situations, and then through a statistical argument, then he shows that we've got problems with that, and so it's a pity, he says, it's a shame that it actually just doesn't work, right? And I think, from my point of view, just thinking about things very simply and looking at the case where the magnets are perfectly aligned or anti-aligned, and you have perfect correlations and perfect anti-correlations, it seems to be that the story of current physics, of the idea that quantum reality is fundamentally random, the story that was promulgated by the Nobel Committee when they granted this prize and the citation, seems to be that these correlations have no explanation, right?
Yes.
They're perfect correlations in this case, but because reality is fundamentally random, they have no explanation. And my question is just like, and I'm just curious about your intuitions here, that just seems absurd to me, because since when do perfect correlations have no explanation, right? So I'm just curious to know what you think, right? And what's your response to that?
I absolutely agree with you. It seems absurd. I thought it was absurd myself for many years. I got very upset about this, and I've been thinking about it for 30 years, I think. And I come to the conclusion that the universe is absurd. And
that's a perfect answer. Thank you very much.
I mean, it just is. It's crazy. Okay, I mean, there are more crazy things we don't understand. I think we're all men here, so I could say, oh, nearly all. Like, I mean, women you can never understand if you're a man, for instance. There are just things which are just beyond humans' understanding. I think I do have a kind of theory about this, because I think that our brains evolved, right? I mean, we used to be fish or lizards, and later we became mammals, and so on and so on. And we've made a very big thing about seeing patterns and acting on them, right? And it's made us into what we are now, about to, destroy our whole planet. Probably the fungus will take over afterwards, so it will be okay in the long run. And we just know that everything that happens does have a cause. That's built into our sort of primary building blocks of cognition. There are some things we just know when we're born, which we need to know when we're born in order to cope with all the inputs which we get and start to organize them and learn more. And the psycholinguistics people call this systems of core knowledge. We have a basic understanding of causality. We have some basic understanding of geometry, space. Causality, I already mentioned. Number, 1, 2, and possibly 3 are built in. And the rest we can figure out after that. And so we always know that when anything happens, it does have a cause. But unfortunately, we're wrong. Too bad. So that's how I think about it.
Yeah, I appreciate that. It distills things down quite nicely. And I would only propose to expand on that in just briefly by saying, we have systems of core knowledge. We almost hardwired, we're almost hardwired to look for causes. Probably all animals are.
Yeah, probably too, yes.
And I think that probably the way of naming what you just identified is the philosophical principle called the principle of sufficient reason.
Yes.
And there's a little bit of work on this by philosophers basically saying, well, quantum randomness defeats the principle of sufficient reason.
Mm-hmm.
And I think that really, in my opinion, that distills the essence of the actual quantum debate here. Is it the case that the principle of sufficient reason is false? Or do we just not understand the deterministic underpinning yet? And that's all I'll say.
That's the choice, and that's why we have Tim coming up with his theory and other people with retro causality and so on and so on. I mean, like the options are kind of getting more narrowing down and getting more extraordinary, I think. But of course, maybe somebody can find out that there's some stupid loophole being overlooked in the latest experiments or whatever, and I shouldn't be thinking of those results, what I think about them. Yeah. Nice question.
Can I answer Adam as well? Please don't forget that all our theories that we use are figments of our imaginations and might not have to do anything with reality.
Yes, but there are theories which work. There is general relativity, there is quantity theory, standard model. So why they are working? They are hidden general relativistic, local realistic. Schrödinger equation is local realistic. How they can work?
They are still models. They are still models.
But somehow they work.
They are corroborated. They are corroborated, but there may be another theory that does exactly the same. We just don't know the other theory. We cannot say special relativity is correct, general relativity is correct.
In some regimes, they work great. So the question still, the bell is says that they shouldn't, they cannot work because they completely different correlations than Bell says. So how these theories, which we know work, somehow work? What is the answer?
I can give you I can show you that special relativity is self-contradictory. Therefore, it cannot.
I completely disagree.
I'll take any bet on it. I'll take any bet on it. You know, I'll send you the paper. I'll send you the paper. But anyway, that's beside the point. But the point is, we cannot the certainty that we are putting onto the theories that have been developed in the last century, or let's say from 1900 onwards, might not be correct. And this is something that we really have to address to understand this all. And then, and that is basically all that I wanted to say to Adam's question that he asked at this stage. Let's get back to the topic of this subject that we have.
I want to add, I think the thing that's missing from this discussion is the uncertainty principle, because we're talking about non-commuting variables, theoretically, and we know that those cannot both be specified exactly by any theory. It's specifically ruled out. And I gave a simple example of how Bell's theorem is violated without any kind of detection loopholes. It's just simple geometry.
So I'm dubious about your example, but I will study.
Why these theories work? And so let me finish. So how do we solve the general relativity? We don't solve it to the Euler-Lagrange trying to unroll the space-time. We solve it through the minimizing the Hilbert-Einstein. So this is the least action principle. On the other side, there are quantum field theories and standard model. We solve it to the ensemble of Feynman diagrams, Feynman trajectories. So in both cases we use time symmetric formulations, and it works. So why cannot we the least action principle, the Feynman ensemble? Why can't we just accept what works? That's my big question.
Well, the reason is because it leads to things which we find incomprehensible. But okay, but if it works, we better get on with using it. And
you are using human intuition that we have evolution from past to future, but maybe humans are wrong. Maybe we are not perfect, and maybe mathematics is right in this case, which says a bit different. Mathematics says that we should use one action optimizing space-time shape, ensemble of histories in space-time. This is mathematics. I don't know how to use evolving Euler-Lagrange for the general relativity. It makes no sense. For quantum field theories, it makes no sense. You have to use these time symmetric formulations to solve the theories which work.
I'm happy to take a crack at it. I've been 30 years on Bell. I do this for pleasure because I just want to understand. Increasingly, forget the metaphysics of life's a dream, and so causality, blah, blah, blah. Start at hermetics with causality stands, even though life's a dream, and above so below. And then to Richard's point, the polarity of male and female is called out in the Hermes Thoth Trismegistus principles, blah, blah, blah. As far as I'm concerned, I've lent my equipment out for Bell because I'm done. I consider myself done. I wanted to see certain things. All that intuition came from the walkers, John and Couder and Emmanuel, and 5 years of looking at them, I'm going like, I'm revisiting Bell with that, right? I do the experiment. My conclusion is, there's probably something with standing waves, or we're full of it. And you're right, Richard. There's nothing there, and we're just deluding ourselves with statistics. Honestly, I still don't understand that argument correctly, but that's on me. As far as I'm concerned, I'm going to dig my hole with experiments. So where I'm at, just to answer the question is, first of all, it needs to be experimental, in my opinion. because I call it the Nobel Tower, or the Tower of Nobel, referencing Babel, right? Everybody has his own opinion. We yell at each other before the wine, and after the wine, we go metaphysical. Great, but we talk about this. And for me, what's really coming out of the walkers is this revival, not just of Bohm, but of De Broglie, because Bohm really had this magical wave function parachuted from the sky. De Broglie is very specific about where it's not specific. He has the wave. I was just reading Dagan and Bush paper, John, that you sent me. Thank you for that. I realized I financed some of it, but I never dived into it. Where you specify the source of the wave, where you specify the interaction of the wave. I think it's called the velocity potential in hydrodynamics. So I can see where you're coming with that. And at the end of the day, to me, the key insight from De Broglie is the standing wave. And Emmanuel, John, and Yves Couder put that back on the map. If you have standing wave, you have really, really interesting things going on. First of all, because you're looking at cavity effects. Second of all, and to me, that's the big thing, it's the special relativity. If you Doppler compress standing wave, not traveling waves, but standing waves, and you assume Compton, meaning the electron standing wave, just like the walkers have a standing wave about them, then you have the proper Lorentz factors. And if we assume, like Feynman, that the internal clock of the electron is the Zitterbewegung, which is a fundamental property, we have no idea, And so what I've been doing for the past year with Herman Batlan at the University of Nebraska is revisit the Guaner experiment that some of you may be familiar with. And it's not the only, we have also recently, Bose-Einstein condensate, but it was the first real experimental evidence of something that looks like the Zitterbewegung clock. Nobody's redone it because nobody talks about it. They had to cheat their way into the Saclay accelerator. So I'm in contact with the team. They're gonna redo it. A new accelerator is coming in Paris. We went with Herman to visit the Frascati accelerator in Italy, in Rome, where Guaner and his team redid the experiment. The equipment is not sufficient. It's not going to work. The Parisian at Orsay are doing a new accelerator, and Denis Dauvergne, who was part of the Guaner team, Guaner died unfortunately last year, is part of the cahier des charges, meaning he's designing the magnets to redo the experiment. And so just to finish on, where do I go personally? That I'm just, this is me. You seem to be doing other more theoretical approaches. I think we need to settle it with experiments. And in fact, there's something in me, because I've been reading a lot of the Rivas models and the Hestenes models following the Guaner rabbit hole, meaning, what is truly the electron, right? We think the electron is this point particle, but obviously if it has so many properties, a mass, a spin, a charge, it has to have extension, just platonically, philosophically speaking, it has to have an extension. What is that structure? We don't know the structure of the electron. The Zitterbewegung is one such hypothesis. And in these models, just to finish with that, there's actually kilo electron volt effects that are really interesting, because Guaner was at 50 mega electron volts, meaning you need a relativistic accelerator to go probe that stuff. But there's actually other effects, which would have to do with this Dirac B-spinner structure of the electron that we could tease. But I'll just finish with, we need experiments. We can't go on with, I think this, I think that. As much fun as this is, I think we need a dramatic new photoelectric effect kind of thing. So I'm all for that. I help finance that and blah, blah, blah. Go ahead. Sorry.
I couldn't agree with you more. And for anybody who hasn't read De Broglie's thesis, there's a translation by Krakauer into the English. But it's very well worth reading, because that standing wave that he sets up is both relativistic and is the thing that derives lambda is h over p, that derives the basis for quantum mechanics. And this is the 1920s, this is before quantum mechanics. This is so crucial to an understanding of what you guys are doing in this, that it cannot not be read. If you've not read it, you haven't studied enough of the literature. If you read French, it's some of the most beautiful French I've ever read, and that includes poetry. It's gorgeous. Read it. That's the first thing. Second thing is, you could not be more right. We need that experiment has to be king here. You have to look at these things in terms of experiment, and experiment is what's kicking out a bunch of talk shit. And there's been a lot of that going on. So experiment is where it needs to go. Guénère experiment is a superb experiment. And it has been repeated in different ways. The Zitterbewegung stuff is very important. CERN doesn't touch, I worked at CERN. These guys, they're so far beyond the energies where you need to study this. I mean, the electron mass 511 keV. So looking at sub that and looking at around that is where experiment needs to go. And there's too little of that kind of experiment being done.
Actually, our problem, John, is finding the accelerator. So
you're right, because the accelerators are too powerful.
It's too powerful. It's not fashionable anymore.
It's not fashionable. I know. We need. Well, that's what we're trying to do with Quisicle. But you should check out my website as well, quisicle.com, because we have a new theory which is relativistic, which does the de Broglie stuff. If you want to have a look at how the stuff has been, well, Martin van der Mark put a paper into, I see into San Diego 2016, which is looking at extending the de Broglie stuff to three-dimensional changes, and that's worth looking at as well. So Chandra, who's online here as well, hosted that conference, and stuff's freely available. It's open source. So if you want, it's also on our website, Quisicle. So perhaps I'll stick up in here if anyone wants to check these things out.
Thank you, John.
Can I just make a comment?
Sure.
So I very much enjoyed the day. Thanks to all the contributors. I just wanted to make a counterpoint to Richard's point. He seemed to suggest that these realist interpretations are getting more and more surreal, if you like. But what I see is and I think what should be the area of focus is the commonality between the various perspectives. So that of Tim, trying to appeal to some chaotic dynamics, that of the Walkers, that of Álvaro, they all seem to suggest chaotic wave-induced correlations. So again, correlations at a distance, not action at a distance. And the Walkers seem to suggest the possibility of this. And this is, I don't follow the jargon, but I am interested in violating Bell with the Walkers. And so this is what we're doing now. We have a static violation. The jury's out even among the co-authors as to whether we'll get a dynamic, whether these correlations will survive once we separate the two subsystems. But we shall see. And again, I think it's very, the fact that the walking droplets evokes de Broglie's mechanics, the fact that it's very closely aligned with Hessene's view. These are commonalities certainly worth exploring as we go further.
Yes, but these classical field theories also still we have this Bell violation problems.
So sorry, say that again.
So this is classical field theory. So I completely agree. I also go this way. The big question, one question is how to get the clock, because this is so like a pendulum. Some oscillation means additional energy. So how to make this? You cannot calm it down to zero. This pendulum of electron kind of, yes. So that's a big question. Another problem is for classical field theorem how to get the Bell violation, especially of these tossing three coins, at least to are equal. So it's completely obvious, but somehow quantum formalism allows for that. So I don't think classical field theory with Euler-Lagrange could allow for that, but if there is action principle, it allows for that.
Experiments will tell us, yes.
But the clock, there is some mechanism for the clock.
Well, yeah, the origin of the clock. I mean, this was sort of proposed by de Broglie, and it's throughout. Even Wilczek's book, The Lightness of Being. He talks.
Yes, but the question is how to get these additional energies. So the question is, usually if you have additional oscillating like pendulum, it wants to come down to zero. The big question is, what propels the clock? Why it does not want to come down to zero for electron? So maybe John, do you have some?
Well, I mean, my view is, physical objects can have resonances like a spring. So if you throw a spring into a turbulent fluid, so if you have some energy in a background field, it will start oscillating at its natural frequency and feed energy into the field at that frequency. And that's the sort of picture we have, which is relevant to the Walker.
Yeah, that's also the Matthew Faber view, and we argue: is it sufficient that to have the resonance, or do we need some proportion, or resonance is sufficient? That's a big question.
Yeah, because they also discuss that also comes up in stochastic electrodynamics. So the question is, they view the particles as an oscillator, which are being excited by the electromagnetic quantum vacuum, and then they again lock onto this picture of the particle as the source of waves. You have a local dynamics that can possibly give rise to non-local correlations.
So this proportion is some noise of vacuum, yes.
No, it comes from the particle's interaction with its own field, which is excited, right? So as in the walkers, you basically have the particle bouncing, it creates its own wave field, and despite the fact that the wave field is symmetric to start with, it goes unstable, then it becomes asymmetric, and so the particle can propagate.
For the bouncer, you have external propulsion. For electron, we need Ising probably.
Sorry, you cut it there.
For the bouncer, you have an external source of energy.
Yeah, driving. Yeah. So that, basically that background energy is playing the role of whatever whatever quantum field is involved.
Yes. So the question is, where is the source? So you are saying that the vacuum noise of the vacuum could be the plus resonance could be the reason for the clock.
And I think another important distinction to make is between de Broglie-Bohm mechanics, which was of course favored by Bell on the grounds that it was non-local, and it's favored by the Bohmian community, and de Broglie's original double solution, which is local. And it's that solution rather than de Broglie-Bohm that's evoked by the walking droplets. So the walking droplets, you're really exploring local pilot wave dynamics and its potential. Yeah.
So how do you violate Bell if you're purely isolated, John?
Through the influence. Okay, so you want to get into it. So we have the static violations. You've seen that paper. Yes. And so Andre Nashbin, who's working with us on this, has done numerics where he considers, and so you guys can all guess what the answer will be. Okay, so you have two walking droplets. Again, they're in a vibrating bath, and they're not communicating. So basically there's a wall in between them, but these two cavities, they're moving, and they move randomly. They're not talking to each other. There's no correlation, okay? Now you do a second experiment. You start the drops together. Now there's a coupling cavity between the two subsystems. And if you start the droplets in that cavity, they will tunnel across and then be stuck in their subsystems. And now, because they're communicating with each other, they go into a very highly correlated energetic state, okay? And so that's no surprise, they're talking to each other. Okay, so then you close the coupling cavity. So you have dynamic topography, which allows you just to slam it shut so they're no longer communicating. You would think, what do you think happens? Do you think it goes back to the state which was obtained in the absence of the coupling, that is to say weakly uncoupled, or does it stay? And it turns out that it stays, okay? And so it actually stays in this highly correlated state, and it's just basically established through the initial conditions, and it persists. So the big question is, these Bell violating states that we found in our first paper on the static test, will those survive isolation? And the jury's out, but there's reason to believe that they might.
Well, if they're correlated, they should still violate, but you're not sidestepping the fact that your preparation is what correlated them. You did not.
No, that's right. That's right. So the point is, you have to then change the measurement settings after the after you separate the subsystems.
And if you do that, you should not. The results should be random.
Should be. We don't know. We don't know. We're going to let nature speak to us, I think.
All right.
Again, even there are 5 authors on the first paper, and we're sort of a hung jury as to whether we think the dynamic test will work. But again, in the spirit of let's see what happens, the walkers have surprised us many times before, and we'll see if they can do it one more time.
I've read Andre's paper, but he points to a transient regime where.
Oh, no, it's not transient. The highly correlated states are persistent.
Persistent. Yeah. Okay.
Thanks.
Is it okay to everyone to upload the videos on YouTube, just in case anyone not like that? I could cut it out, but otherwise,
we'll cut to the end of the last talk, and if somebody would not like us to be there, so we can cut out it. Please let us know. Okay, so maybe you can go to the questions. Maybe if there is.
Can you clarify what part did you need to cut out?
Well, just in case someone didn't want to appear on YouTube, I could cut out that part. Just
let us know. Okay, so maybe we can go to the questions. If there is no discussion as you want. So
isn't that what we were doing?
I read John Bush's article, I think the one I posted in 2014, and was amazed that you're here today, John. It's about the fluid systems, quantum mechanics. You're mentioned in it.
Thank you.
Okay, so maybe we can discuss. There was a discussion about the Stern-Gerlach experiment. Can we see measurement this way? Maybe let me show this slide. Okay, so there is this slide. So there is a basic problem of understanding quantum mechanics is the measurement, and there is this Stern-Gerlach, I think, well acknowledged idealization, and so then there is this magnetic dipole aligns in a external magnetic field. So there is classical understanding that if it aligns, then the torque goes to zero. Then so we have no longer the Larmor precession. So the energy can be minimized if it's aligned. And there was this discussion about this paper. This semi-classical. So this term uses Dirac equation, and he got Sergey. He got alignment. Generally, so in this alignment, there should be radiation of this excessive energy. Also, looking at the Poynting vector, there is some non-zero radiation until it is aligned. But we cannot observe this photon, and the suggestion is that the electromagnetic wave should be cylindrically symmetric, because this is a cylindrically symmetric system. So maybe it's not optical photon, but some EM wave cylindrically symmetric. So what do you think about measurement, about Stern-Gerlach? Any ideas here? Comments?
So what are you trying to show here? That this system is completely dynamic. We're not talking about intrinsic spin. The spin is always the result of an interaction with an external.
We think about the object as a magnetic dipole, some tiny magnet.
Right, tiny magnets. And there's no such thing as a spin up, spin down. There's a spin in any direction. And then when we add in one direction, we force the outcome.
Yes, so if the spin is not aligned, then we get the Larmor precession.
Okay, and your point is that if we should see some radiation, is that what you're saying?
Yeah, so I'm saying yes. So there is no Larmor precession if it's aligned. If the torque goes to zero, what is for parallel or anti-parallel? Yes, and if it's not, then Larmor precession means additional kinetic energy.
I see.
And so we can look at that as excited atom goes to the excited atom radiating the excessive energy.
So one of the experts modern on Stern-Gerlach is Herman Batlan at the University of Nebraska. Is writing extensively about this. I think you're right that it always struck me that Stern-Gerlach points to no elements of reality a la Einstein. There is no such thing as intrinsic spin. The result of, I mean, there is a physical thing going like this, but it's not up or down. That's when we force it up or down. It's a great example of the contextuality where the measure forces alignment
exactly
one way or the other. That's a great point. I agree with that.
Yes.
And then if you think, but we should see extra radiation out, then think about how to see it and run it by somebody like Herman.
Okay, so the question, so first question is, should there be extra radiation? And I'm saying that there should be energy difference. Because initially there is kinetic energy of Larmor precession, and finally there is no kinetic energy. So this difference of energy should be radiated, for example, as electromagnetic wave. Also, there is a difference in angular momentum. Initially, it is a random direction, and finally, it's aligned direction. So there is difference of angular momentum. So these two differences should be radiated through some electromagnetic wave.
Okay, makes sense.
Yeah, makes sense. Yes. So another argument is that you're looking
calculate it, make a simulation, calculate it, like get it, put a number there.
So there are. So here is this Sergei Rajnitsky, something like that article we have discussed on the web page, the mailing list, and he claims like 10 to minus 9 seconds. Another argument is this Poynting vector, this energy density of radiated energy. So if the dipole is static, then you have only magnetic field, no electric field. But if it's moving, then the electric field appears from Maxwell equation. So there should be this radiation. So the question about the experimental observation is the problem that in the excitation we have a photon, we have a localized photon, but here we should rather have cylindrically symmetric electromagnetic wave. So it should be not localized. Energy density should drop with 1 over square root of s squared radius. Yes. So the question is how to observe these radiations. It might be only through some heat transfer, but it might be very difficult to observe.
I have no idea.
Yes, so it should. I think it shouldn't be photon. It shouldn't be localized. So atom absorption might be, but maybe some, I don't know, some heat transfer. I don't know. And this way also it could be reversible. But the problem is how to prepare this reversed electromagnetic wave. So, but in theory it should be reversible process.
Jarek, I think you must distinguish between electromagnetic waves as in radio waves, as you have shown here, that would be the sort of field around the dipole antenna, and photons. I have been, I don't know how many hours I've thought about how does a transition of the electrons, which happens instantaneously, come into a light wave with a certain frequency, and we must not model light waves or photons in terms of radio waves. We must have light waves.
That's another discussion we recently had at the mailing list. Yes, so are photons always quantized? That's a big question, and for example, so one argument that they are not is this SPDC, spontaneous parametric down conversion, when you increase the number of photons. So you cannot say that there is some fixed number of photons because the number increases in SPDC. So I think that there are two types. So antenna and laser is kind of similar to antenna. Is different than single atom, the excitation, single atom sources. Yeah, so.
I don't accept your idea that this doubling of photons is not dynamic. So one photon enters and it interacts with a complicated system, and then this complicated system emits 2 photons. So this is not contradicting.
So yes, so you're saying that this so there's minus 1 photon inside this nonlinear crystal. Yes, so
yes. That's what is Chandra is insisting always, that you have to take into account the interaction of your system, your photon with the rest of the world.
So using this argument, I can say that setting continuous light beam through SPDC, it should be finally filled with these minus photons. So there should be some change inside this crystal, no?
Yes. In the crystal happens something. very complicated, and 2 photons come out.
Well, isn't it in the crystal? It's basically you get a atomic excitation, or electron excitation, or maybe a crystal excitation with the incoming laser, and that goes through a 2-photon cascade, like in the calcium atomic cascade, which gives us 2 beams. Now, basically, you know, it is difficult to explain. I see this here. It's in 2 weeks' time. I will answer all these questions to you. You know,
exactly. It happens like this. You make an excitation, and then you go down via an intermediate state. That's it.
Correct.
Yes. So it's completely understandable in atomic physics.
Yes.
But I think there are different sources.
And can I just interrupt here? And the difference to the calcium 2 cascade, where the calcium atom is static, there is no transfer of momentum or rotation. That's why the 2 photons go off at 180 degrees, as described, as were used in the early experiments. And in the nonlinear crystal, you have momentum conservation from the incoming beam, which needs to be conserved to the outgoing beam. And that's why you have the 2 beams going out. And then you get the separation, up and down, the 2 ways, so that the momentum up is equal to the momentum down. So if we look at the type 2 crystal, where we have these 2 circles, if you take the central point where the incoming beam is, you will always find entangled photons on the what would you call it, on a straight line that goes from either circle, from the one circle to the other circle. You know, it's a simple. I see this simply as conservation of momentum and etc. You know, and an atomic cascade. Now, to discuss this, but I will go into this very deeply in 2 weeks' time. You know, so it's difficult for me to explain this all, because I need to get you up to date with my thinking, which is basically I'm introducing a new ontology. And you know, it's not classical and it's not modern.
Sure. Okay, so regarding the direction of spin, also for electron, if you use the B-spinor, B-spinor encodes direction in 3D of the spin. So I think it's ordinarily a continuous angle, and during the measurement, it aligns due to conditions like magnetic field.
Slow down, Jarek, because that's super interesting. Let's say you're right that the B-spinor is an actual random orientation, and what we call spin up and spin down is not intrinsic to the electron, but is a result of the measurement with a field that comes out either up and down. I like to talk about it in terms of political opinion. Our political opinions may be all over the map, but we're asked to vote along left or right measurement apparatus, and there's no intrinsic left or right. There's just the measure that gives us left or right. So I'm good with that. The thing that I saw on your slide that I want to dig into a little bit, you said difficult to observe because it's going to dissipate as heat. Are you sure? Is it not going to be an electron? Because you just have an electron floating going. Heat is a property of electrons. So you need a lattice of electrons for the heat to move. Wouldn't it be a photon that is emitted? I'm trying to get a detection of this thing for you.
Yes, so I'm saying that I think there are two types of electromagnetic waves. So one type are from antenna, which for example can be cylindrically symmetric. And there was we had this discussion, this many clips of this experiment that this guy has this very weak laser, and he calculated it should be one photon, and turns out this one photon still may interference. And the explanation was that it was not indeed one photons, but it was sinusoid amplitude of very tiny amplitude. So
very tiny amplitude. And do you have an idea of this amplitude? Like,
so,
can you
yes,
quantify
also,
what it means?
also here,
yeah.
Also here, you don't have single photons. You have only reduction of amplitude with distance because of the power conservation. So this is different type of electromagnetic pulse than optical photon. So it is not localized optical pulse. It is not localized electromagnetic wave.
So there's a
the question is
dissipation of that energy.
So yeah, so I think it finally it would become noise. So it would turn into heat practically.
Okay,
so
number one, put an order of magnitude on this thing. Like when you know we know the spin energy.
I think like atomic energies.
Atomic transition. So photons, you said no.
That electron-volt energy, but not localized, but delocalized, which will be cylindrically symmetric impulse. Electromagnetic.
How do you do? And what's that amplitude? Do you know? Energy-wise, like a scale of energy.
Energy. I think electron volts.
Electron volts. And do we know how to detect electron volts around flying electrons? You know, that would dissipate that energy around.
If it is in vacuum, if finally maybe some calorimeter could check it. I don't know.
Some kind of what?
Calorimeter for calculation.
Calorimeter.
Yeah, but it's too tiny, I think. So
is there a notion of heat for a single electron? Well, I always associate heat to lattice, you know, energy movement, meaning a condensed matter thing, not an inherent property.
No, heat is energy per degree of freedom.
Yeah. Okay, whatever. All right. Order of magnitude EV and detecting, I don't know, I'm happy like pinging Herman and going like, hey, let me take a picture of this.
Jarek, how are you proposing that the entanglement would happen with two of these dipoles?
So yes, this is a big problem. So also, if you look at this Sergey article, so he says there is a condition is super simple, but there is some critical angle he can calculate, and if the initial angle is above this critical angle, then it will align up, and if it's below, then it will align down. So for me, it's suspicious.
I don't think it has anything to do with entanglement, but just it goes.
Yeah, I don't believe you can get Bell violation with this kind of
thing. That's a different, but you know, cool.
But
well, that gets to what my talk was about. Yeah, if you just have the entanglement be a boundary that if this oh, you can't see my cursor, but yeah, if that angle gets to 90 degrees, then it changes sign. That doesn't work. But if you can get the entanglement such that the entanglement fixes the azimuthal angle phi in such a way that the value, the boundary is a constant value of phi rather than theta equals 90 degrees, then you can get the Bell violation. You following that?
I don't think you can get Bell violation here. So not in this simple way. So my answer is that nature solves it through this kind of classical field theory, through the least action principle.
Yeah.
And this way you can get the violation, no problem. But if you think about Euler-Lagrange, then I think you cannot get the violation.
Well, can I show my slide again? I'll show you what I mean by that. This one. So here, if these are your two measurement angles from your Stern-Gerlach, if you can entangle the two electrons such that the boundary between plus and minus is a constant value of azimuthal angle phi, as opposed to what's more commonly people think of is that you have the boundary be theta equals 90 degrees, the horizontal plane here. If you fix the azimuthal angle and have the boundary be a different azimuthal angle, then you get the Bell violation. So it's a question of how you do the entanglement.
Yes, so I have just put in the chat this Sergey article. So if you look there, there is super simple equation condition that if angle is 25, equation 25, if angle is above some critical, then it will align up. If it's below, it will align down. Super simple condition. I think it's too simple, but
Yeah.
it is not.
Robert,
Equation 25.
Robert, you entangle two electrons, and then in the end you said, how do we entangle two electrons? Now, in my opinion, entanglement is a conservation of state, or it is more than just conservation of energy. It's conservation of fluxes of the electromagnetic spectrum. And that is what needs to be found. That's without knowing the physics, what causes entanglements, everything comes down to these probabilistic discussions, and the deniers who bring up huge loopholes, which themselves do not make sense, which are even more absurd than what the Bell inequality tells is, because we don't want to believe in this in a non-causal system. So I think that is where we need to look at, and to understand this all better.
Yeah, I agree. So I show what the geometry would be for Bell violation, for two measurement angles, as in the spin correlations. But the question is, how does that relate to an actual measurement? Maybe it's not the physical space, but maybe it's momentum space or something, or spin space. So there's a geometrical picture, but doesn't tell you what the dynamical picture is.
Chandra has written that Sergey might give a talk in April, so we can discuss.
Yes, I asked him. He will give it. He's willing to give a talk in April, so we can maybe influence him what he would talk about. But he has actually several really interesting papers, I think.
Yes.
Could you put a reference in the chat to your paper?
The Stenger I have put, but if you just search for.
Yeah, well, my slides are listed in the description for this conference. I did publish a paper years ago, but using a kind of different model, so I think it's less intuitive. I think actually the slides are a better explanation.
But I would like to see your picture of this sphere and your interpretation. Can you give a reference? Just put it in the chat.
Sure, but it's in the slides. If you just look up the Google Doc describing this meeting, it's in my slides there.
Okay, so I'll have to look up afterwards.
All right, yeah, I'll try to find that.
You can send me an email also, no problem.
Oh, okay.
I've just put my latest paper into the chat, which will basically be will also be discussed in 2 weeks' time. But there I define the requirements of entanglement. So from a purely mathematical point of view, and satisfying the Maxwell equations.
I put the link in the chat.
Thank you very much. I saw it. Let's just go into it.
Okay, so maybe you can quickly go through the questions, maybe. Also close to, okay, the 5th. Okay, ask you answer. Sure. You can finish for today, or I don't know.
Okay, thank you.
Okay.
Jarek and Chantal, thank you very much. It was a very stimulating afternoon.
Thanks. Thanks.
Well, thank you very much for your time. It's really interesting.
Thank you. Have a nice Sunday. See you next time.
Bye.
Bye. Thanks.
Bye.